Imagine this: two colossal, mysterious bubbles stretching tens of thousands of light years above and below the Milky Way's core. They're invisible to the naked eye but glow brilliantly in gamma rays, the highest energy form of light. These structures, known as Fermi Bubbles, have puzzled astronomers since their discovery in 2010. They're immense, powerful, and full of secrets we're only beginning to uncover. What could create such massive, high-energy phenomena in the heart of our galaxy? Are they remnants of violent cosmic events, or could they be evidence of something entirely new? By the end of this exploration, you'll see why these enigmatic bubbles are more than just a curiosity. They might hold the key to understanding the very forces shaping our galaxy. Fermi bubbles are unlike anything else we've found in space. Spanning about 50,000 light-years in diameter, these massive structures dwarf even the most energetic supernova explosions. They radiate in gamma rays, a type of light that's typically associated with some of the universe's most extreme processes. Think black holes, neutron stars, or particle collisions happening at nearly the speed of light. But the Fermi bubbles aren't just bursts of energy. They're structured, coherent shapes, extending symmetrically above and below the Milky Way's galactic plane. Their very existence challenges our understanding of how galaxies work. Let's talk about their discovery. Back in 2010, the Fermi Gamma-ray Space Telescope was scanning the sky, as it had been doing since its launch in 2008. It was designed to map gamma-ray sources and phenomena, but no one was expecting what it found near the center of the Milky Way. The telescope detected two enormous lobes of gamma-ray emission, extending outward in opposite directions from the galaxy's core. At first, researchers weren't even sure what they were seeing. Were these anomalies errors in the data? Interference from some Earth-based source? But as the data piled up, one thing became clear: the Fermi bubbles were real, and they were extraordinary. The size of these bubbles is hard to comprehend. To put it into perspective, if they were visible in the night sky, they would stretch across a region roughly 40 times the size of the full moon. They aren't just wide, they're tall, stretching tens of thousands of light years above and below the galactic plane. And they're shockingly symmetrical, almost like a mirror image of each other. This symmetry is one of the first clues about their origins. It suggests that whatever created them was both powerful and centrally located in the galaxy. Now, here's where it gets even more fascinating. The Fermi bubbles aren't just emitting gamma rays. They're also associated with X-rays, radio waves, and even microwaves. This multi-wavelength presence means they're interacting with all kinds of particles and forces in space. Scientists studying these emissions have noticed that the bubbles are filled with high-energy particles traveling close to the speed of light. These particles are likely interacting with magnetic fields, generating the gamma rays we detect. But where did these particles come from? And what kind of force could accelerate them to such extreme speeds? One leading theory is that the Fermi bubbles are the aftermath of a massive outburst from the Milky Way's central supermassive black hole, Sagittarius A star. Black holes aren't just cosmic vacuum cleaners. They can also launch incredibly energetic jets of particles and radiation when matter falls into them. If, at some point in the past, Sagittarius A* had a feast of gas or stars, it could have erupted in a powerful event, blasting material outward and creating the Fermi bubbles we see today. The symmetry of the bubbles fits this idea. Such outbursts are often directional, with jets shooting out in opposite directions along the black hole's axis of rotation. But there's another possibility. The Fermi bubbles might be the remnants of intense star formation near the galactic center. When stars form in large numbers, especially massive stars, they produce winds of charged particles and, eventually, supernova explosions. These collective forces can create superbubbles of energy, pushing out matter and radiation on a galactic scale. If this is the case, the Fermi bubbles could represent a snapshot of our galaxy's violent past, a time when star formation near the core was happening at an unprecedented rate. Interestingly, the age of the Fermi bubbles is still a topic of debate. Some estimates suggest they're a few million years old, while others place their formation closer to 10 million years ago. Determining their age could help narrow down their origin, whether they were created by black hole activity, star formation, or some other process. The bubbles also appear to be expanding, though the exact mechanism driving their expansion remains unclear. Another mystery is the composition of the Fermi bubbles. They're not just empty space filled with radiation, they contain matter, magnetic fields, and high-energy particles. Scientists are still trying to figure out exactly what's inside them and how those components interact. For example, the edges of the bubbles seem to be defined by a sharp boundary, which could indicate some kind of shockwave or interaction with the surrounding interstellar medium. This boundary might hold clues about the forces that created and shaped the bubbles. One of the most perplexing aspects of the Fermi bubbles is their apparent lack of correlation with other known structures in the Milky Way. For example, they don't seem to be directly connected to the galaxy's spiral arms or its overall star distribution. This independence makes them even harder to explain. Are they a unique feature of our galaxy, or could similar structures exist in other galaxies, waiting to be discovered? Speaking of other galaxies, there's some evidence that similar phenomena might exist elsewhere. Observations of nearby galaxies like M31, the Andromeda Galaxy, and M82, a starburst galaxy, have revealed features that resemble the Fermi bubbles, though on smaller scales. If these structures are indeed common, it could mean they're a natural byproduct of galactic evolution. But if they're rare, it could point to something unusual or unique about the Milky Way. The Fermi bubbles also raise questions about the broader role of gamma rays in the universe. Gamma-ray astronomy is a relatively young field, and every new discovery seems to challenge our assumptions. What other surprises might be lurking in the gamma-ray sky, hidden in plain sight? Could the processes that created the Fermi bubbles also be responsible for other mysterious phenomena, like cosmic rays or the enigmatic glow of diffuse gamma radiation that permeates the universe? The implications of the Fermi bubbles extend far beyond the Milky Way. If these enormous structures are tied to the activity of Sagittarius A*, they provide a window into the behavior of supermassive black holes, which are thought to exist at the center of nearly every large galaxy in the universe. Black holes are some of the most enigmatic and powerful objects in existence, capable of shaping the galaxies around them through their immense gravitational pull and energetic outbursts. Understanding the Fermi bubbles might help us decode how these cosmic giants influence their surroundings. Take the concept of feedback, for instance. In astronomy, feedback refers to the way energy and matter expelled by a black hole or star formation can regulate further activity. For example, an outburst from Sagittarius A* could have expelled gas and dust from the galactic center, potentially slowing down or halting star formation in that region. This self-regulating process is thought to play a critical role in the evolution of galaxies, preventing them from becoming overly dense or too active. If the Fermi bubbles are indeed the result of such feedback, they might represent a snapshot of this delicate balancing act in action. But what if the origin of the Fermi bubbles is more exotic? Some scientists have speculated that these structures could be the result of dark matter interactions. Dark matter is one of the greatest mysteries in modern science, an invisible form of matter that makes up about 27% of the universe's total mass and energy. It doesn't emit, absorb, or reflect light, making it incredibly difficult to detect. However, some theories suggest that dark matter particles could annihilate or decay in ways that produce gamma rays. If this is the case, the Fermi bubbles might be a massive clue pointing toward the elusive nature of dark matter. The idea of dark matter being involved is particularly intriguing because it could help explain the unique gamma-ray signature of the Fermi bubbles. The energy levels of the gamma rays emitted by these structures don't quite match what we would expect from typical astrophysical processes like black hole jets or supernova explosions. This mismatch has led some researchers to propose that something more fundamental, and potentially groundbreaking, might be at work. If dark matter is indeed responsible, the Fermi bubbles could be our first direct evidence of this mysterious substance. On the other hand, there's also the possibility that the Fermi bubbles are a kind of cosmic relic, left over from a period of intense activity in the Milky Way's past. Some studies have suggested that the gamma-ray glow might be related to ancient cosmic rays, particles that were accelerated to near light speeds millions of years ago, and have since become trapped within the bubbles. These particles could have been launched by any number of energetic events, from black hole outbursts to waves of star formation. If this theory is correct, the Fermi bubbles could act as a sort of time capsule, preserving a record of the Milky Way's turbulent history. The mystery of the Fermi bubbles also raises questions about the role of magnetic fields in shaping galaxies. Magnetic fields are a critical but often overlooked component of the universe, influencing the movement of charged particles and the structure of interstellar gas. Observations suggest that the Fermi bubbles are threaded with magnetic fields, which could be helping to contain the high-energy particles inside them. These fields might also explain the sharp edges of the bubbles, acting as barriers that prevent the particles from escaping into the surrounding galaxy. By studying these magnetic fields, scientists can gain new insights into how energy and matter interact on a galactic scale. As research into the Fermi bubbles continues, astronomers are also exploring their connection to other mysterious phenomena in the Milky Way. One intriguing possibility is that the bubbles are linked to the so-called galactic center excess, a puzzling surplus of gamma rays detected near the core of the galaxy. This excess has defied easy explanation, with theories ranging from dark matter interactions to populations of millisecond pulsars. Some scientists believe that the Fermi bubbles and the galactic center excess might be two sides of the same coin, both stemming from the same underlying processes. The Fermi bubbles are also helping to refine our understanding of cosmic jets and outflows, which are common features of galaxies with active black holes. These jets can stretch for millions of light years, carrying enormous amounts of energy and matter away from their host galaxies. While the Fermi bubbles aren't quite the same as these jets, they share many similarities, such as their symmetrical shape and high-energy emissions. By studying the bubbles, astronomers can test models of how jets and outflows form, evolve, and interact with their environments. One of the most exciting aspects of studying the Fermi bubbles is the potential for future discoveries. Advances in telescope technology, such as the upcoming Cherenkov telescope array, promise to provide even more detailed observations of gamma-ray sources. These instruments could reveal new features of the Fermi bubbles, such as fine structures or variations in their emissions, that could help unravel their origins. They might also detect similar structures in other galaxies, providing a broader context for understanding these phenomena. The Fermi bubbles are a testament to the fact that the universe is still full of surprises. Despite decades of exploring the cosmos, we're constantly finding new puzzles that challenge our understanding of how the universe works. The discovery of these enigmatic structures has opened up a whole new field of research, bridging topics as diverse as black hole physics, cosmic ray acceleration, and dark matter. Each new piece of data brings us closer to understanding these incredible phenomena, but also raises new questions, ensuring that the mystery of the Fermi bubbles will continue to captivate scientists and the public alike. The Fermi bubbles remind us of the vastness and complexity of the universe. They're a stark reminder that even in our own galactic backyard, there are wonders we have yet to fully comprehend. Whether they're the remnants of a black hole's tantrum, the echoes of ancient star formation, or something entirely unexpected, the Fermi bubbles stand as a monument to the mysteries of the cosmos, and to humanity's relentless quest to uncover them. To truly grasp the magnitude of the Fermi bubbles, we must delve deeper into the scientific techniques and tools that have allowed astronomers to study them in such detail. These bubbles, stretching approximately 25,000 light-years above and below the Milky Way's galactic plane, present unique challenges for observation. Gamma rays, the high-energy form of electromagnetic radiation that defines the Fermi bubbles, cannot be observed with traditional optical telescopes. Instead, specialized instruments like the Fermi Gamma-ray Space Telescope play a pivotal role in unlocking their secrets. The Fermi Telescope, launched in 2008, has revolutionized our ability to study high-energy phenomena in the universe. Its Large Area Telescope, LAT, is capable of detecting gamma rays with unprecedented sensitivity and resolution, providing a detailed map of the sky in this energetic wavelength. The discovery of the Fermi bubbles in 2010 was a direct result of this advanced technology. The LAT revealed two massive, balloon-like structures extending symmetrically from the galactic center, glowing brightly in gamma rays and standing out starkly against the cosmic background. What makes the Fermi bubbles so intriguing is not just their size but also their sharp edges. These boundaries suggest that the bubbles are well-defined structures, with a clear separation from the surrounding interstellar medium. This sharpness poses a fascinating question: what mechanisms are keeping the bubbles so well contained? One possibility is that magnetic fields within the bubbles are acting like a protective barrier, trapping high-energy particles inside and preventing them from diffusing outward. This hypothesis aligns with observations of polarized emissions, which indicate the presence of ordered magnetic fields threading through the bubbles. Understanding the energy source behind the Fermi bubbles is another key puzzle. The amount of energy required to create these structures is staggering, estimated to be equivalent to the energy output of about 100,000 supernovae. This immense energy budget points to a highly energetic and sustained event in the Milky Way's history. One leading theory is that the bubbles were formed by an outburst from Sagittarius A*, the supermassive black hole at the galaxy's core. If true, this outburst would have occurred several million years ago, releasing a torrent of energy that carved out these massive structures. To put this in perspective, consider the scale of the Fermi bubbles. Each bubble spans roughly 1/4 of the Milky Way's diameter, dwarfing the central region of the galaxy from which they emanate. The symmetry of these structures suggests a common origin, likely tied to the central black hole, or a synchronized wave of star formation. If Sagittarius A* was indeed the source, this event would represent a phase of intense activity, far more energetic than the relatively quiescent state we observe today. Interestingly, the Fermi bubbles are not alone in exhibiting such large-scale outflows. Similar structures have been observed in other galaxies, particularly those with active galactic nuclei, AGN. AGN are powered by supermassive black holes that actively accrete matter, producing jets and outflows that can extend for hundreds of thousands of light years. While the Fermi bubbles are not as extreme as the jets seen in AGN, their existence suggests that even relatively quiet galaxies like the Milky Way can experience periods of heightened activity. This realization broadens our understanding of galactic evolution, showing that even dormant black holes can leave a lasting imprint on their host galaxies. One of the most captivating aspects of the Fermi bubbles is their potential connection to cosmic rays. These high-energy particles, which include protons, electrons, and atomic nuclei, are constantly bombarding Earth from space. The Fermi bubbles are thought to be filled with cosmic rays that were accelerated to near-light speeds by shock waves or magnetic turbulence. As these particles interact with the interstellar medium, they produce gamma rays, contributing to the bubble's bright emission. Studying these interactions provides valuable insights into the mechanisms of particle acceleration, a topic with implications that extend far beyond our galaxy. In addition to their gamma-ray glow, the Fermi bubbles also emit X-rays, suggesting a multi-wavelength approach is essential for fully understanding them. Observations from X-ray telescopes like NASA's Chandra X-ray Observatory have revealed hot gas within the bubbles, with temperatures reaching tens of millions of degrees. This hot gas could be the remnants of the original outburst, still cooling and expanding long after the initial event. The combination of gamma-ray and X-ray data paints a more complete picture of the bubble's composition and energy dynamics, helping scientists piece together their enigmatic history. Despite the wealth of data gathered so far, many questions about the Fermi bubbles remain unanswered. For example, what triggered the initial outburst that created them? Was it a sudden influx of matter into Sagittarius A*, sparking a violent release of energy? Or was it a burst of star formation near the galactic center, with massive stars exploding as supernovae in rapid succession? These scenarios are not mutually exclusive, and it's possible that multiple processes contributed to the formation of the bubbles. Another mystery lies in the timescale of the Fermi bubbles' existence. Current estimates suggest they are millions of years old, but how long will they persist? Will they eventually dissipate as the high-energy particles within them lose their momentum? Or will they remain as a permanent feature of the Milky Way? Answering these questions requires long-term observations and detailed modeling, both of which are ongoing. The Fermi bubbles also challenge us to think about the broader implications of their existence. If similar structures exist in other galaxies, what can they tell us about the life cycles of galaxies as a whole? Are the Fermi bubbles a common phase in the evolution of spiral galaxies like the Milky Way, or are they a rare and exceptional phenomenon? By studying these bubbles in the context of other galaxies, astronomers can begin to piece together a more unified theory of galactic evolution. As we look to the future, the study of the Fermi bubbles is set to benefit from a new generation of telescopes and observational techniques. Instruments like the Square Kilometre Array, SKA, and the James Webb Space Telescope, JWST, will provide unprecedented sensitivity and resolution, allowing scientists to probe the bubbles in greater detail than ever before. These advancements will not only enhance our understanding of the Fermi bubbles but also open up new avenues for exploring the high-energy universe. The story of the Fermi bubbles is far from over. These enigmatic structures continue to captivate scientists and the public alike, serving as a powerful reminder of the mysteries that still lie hidden in the cosmos. They are a testament to the power of modern astronomy, showing how cutting-edge technology and creative thinking can unravel the secrets of the universe. Yet, for all we've learned, the Fermi bubbles remain a puzzle, a tantalizing glimpse of the forces that shape our galaxy and, perhaps, the universe itself. The ongoing study of the Fermi bubbles has also spurred significant advancements in theoretical modeling. Scientists use sophisticated simulations to recreate the conditions that might have led to the formation of these massive structures. These models incorporate various physical processes, such as black hole accretion, shock waves, magnetic fields, and cosmic ray propagation. By comparing the outputs of these simulations to observational data, researchers can refine their understanding of the dynamics within the bubbles. One promising area of investigation focuses on the interaction between the Fermi bubbles and the surrounding interstellar medium. The edges of the bubbles are surprisingly well defined, suggesting that some mechanism is confining the high-energy particles within them. This confinement could be the result of shock waves created by the initial outburst, compressing the surrounding gas and forming a barrier. Alternatively, magnetic fields could play a key role, acting like an invisible cage that traps particles inside the bubbles. Understanding these interactions requires a delicate balance of observational data and theoretical analysis, highlighting the collaborative nature of modern astronomy. Another fascinating aspect of the Fermi bubbles is their potential to illuminate the history of the Milky Way's central region. The supermassive black hole at the heart of our galaxy, Sagittarius A*, is currently in a relatively quiescent state, with only occasional flares of activity. However, the existence of the Fermi bubbles suggests that this was not always the case. If the bubbles were indeed formed by an outburst from Sagittarius A*, this event would mark a period of intense activity millions of years ago, when the black hole was accreting matter at a much higher rate. This raises intriguing questions about the life cycle of supermassive black holes. Do all black holes go through periods of dormancy and activity, or are some more stable over time? If Sagittarius A* was more active in the past, what caused it to enter its current phase of relative calm? These questions are not just relevant to our galaxy but also to the broader study of supermassive black holes and their role in shaping the universe. By studying the Fermi bubbles, scientists can gain insights into the feedback processes that occur when black holes interact with their host galaxies. The energy required to create the Fermi bubbles is another area of active research. Current estimates suggest that the total energy involved is on the order of 10 to the power of 56 ergs, a truly staggering amount. To put this into perspective, this is equivalent to the energy released by hundreds of thousands of supernovae. Such an enormous energy budget rules out many potential sources, leaving only the most extreme astrophysical processes as viable candidates. Whether this energy came from a black hole outburst, a burst of star formation, or some combination of the two, its sheer magnitude underscores the dramatic events that have shaped our galaxy's history. One particularly intriguing hypothesis is that the Fermi bubbles are the remnants of a starburst event, a period of rapid star formation near the galactic center. During such events, massive stars are born in large numbers and then quickly exhaust their fuel, ending their lives in powerful supernova explosions. These explosions release vast amounts of energy, which could drive the formation of structures like the Fermi bubbles. If this scenario is correct, the bubbles would serve as a kind of fossil record, preserving evidence of a starburst event that occurred millions of years ago. Another possibility is that the bubbles were created by jets of material ejected from Sagittarius A star. While our galaxy's central black hole is not currently producing such jets, Many other galaxies with active galactic nuclei exhibit this behavior. These jets, composed of high-energy particles traveling at nearly the speed of light, can extend for hundreds of thousands of light-years, carrying energy and momentum far from the black hole itself. If Sagittarius A** produced similar jets in the past, they could have inflated the Fermi bubbles, leaving behind the structures we observe today. Beyond their origins, the Fermi bubbles also have implications for the broader field of high-energy astrophysics. The gamma rays emitted by the bubbles are thought to result from interactions between cosmic rays and the interstellar medium. These cosmic rays are high-energy particles that are accelerated to near-light speeds by shock waves or magnetic turbulence. By studying the Fermi bubbles, scientists can gain valuable insights into the processes that accelerate these particles, which are also responsible for many other high-energy phenomena in the universe. The Fermi bubbles also provide a unique laboratory for studying the interplay between magnetic fields and charged particles. Magnetic fields are notoriously difficult to measure directly, but their effects can be inferred from the behavior of particles and emissions within the bubbles. For example, polarized light emissions can reveal the orientation and strength of magnetic fields, offering clues about their role in shaping the bubbles. Understanding these dynamics is crucial not only for studying the Fermi bubbles but also for broader questions about the role of magnetic fields in the cosmos. Despite the progress made so far, the Fermi bubbles remain a tantalizing mystery, with many questions still unanswered. For instance, why are the bubbles so symmetrical? This symmetry suggests a highly organized and centralized energy source, but the exact nature of this source is still debated. Additionally, what role do the bubbles play in the larger ecosystem of the Milky Way? Do they influence star formation, gas dynamics, or the distribution of cosmic rays in the galaxy? These questions are at the forefront of current research, driving new observations and theoretical studies. As technology continues to advance, the study of the Fermi bubbles is poised to enter a new era. Future space telescopes, such as the Cherenkov Telescope Array (CTA), and the proposed Advanced Telescope for High-Energy Astrophysics, Athena, will provide even greater sensitivity and resolution in the gamma-ray and X-ray regimes. These instruments will allow scientists to probe the bubbles in unprecedented detail, uncovering new features and refining our understanding of their origins and evolution. Moreover, the Fermi bubbles serve as a powerful reminder of the interconnectedness of cosmic phenomena. Their study bridges multiple fields of astrophysics, from black hole physics and star formation to cosmic ray acceleration and magnetic field dynamics. By unraveling the mysteries of the Fermi bubbles, we not only learn more about our own galaxy but also gain insights into the universal processes that shape the cosmos. The Fermi bubbles are a testament to the enduring mystery and beauty of the universe. They challenge us to think beyond our current understanding, to question our assumptions, and to seek out new explanations for the phenomena we observe. They are a symbol of the unknown, a reminder that, no matter how much we learn, there is always more to discover. The Fermi bubbles also offer a unique opportunity to study the life cycle of energy within the galaxy. These enormous structures may act as a kind of cosmic recycling mechanism, where energy released in catastrophic events is redistributed throughout the Milky Way. This redistribution of energy can affect everything from the motion of interstellar gas to the rate of star formation in regions far from the galactic core. In this sense, the Fermi bubbles are not just relics of past events. They are active participants in the ongoing evolution of our galaxy. One of the most intriguing aspects of this energy redistribution is its potential impact on the cosmic rays that permeate the Milky Way. Cosmic rays are high-energy particles that travel through space, often interacting with gas, dust, and magnetic fields. The Fermi bubbles, with their high-energy gamma-ray emissions, are thought to be a key source of these cosmic rays. By studying the bubbles, researchers hope to better understand how cosmic rays are generated, accelerated, and distributed throughout the galaxy. The gamma rays emitted by the Fermi bubbles also provide critical clues about the processes occurring within them. Gamma rays are the most energetic form of electromagnetic radiation, and their production often involves highly energetic events or interactions. In the case of the Fermi bubbles, one leading theory is that the gamma rays are produced when high-energy electrons collide with low-energy photons in a process known as inverse Compton scattering. This interaction boosts the energy of the photons into the gamma-ray range, creating the emissions observed by the Fermi Gamma-Ray Space Telescope. Another possibility is that the gamma rays are produced through the decay of neutral pions, which are created when cosmic rays collide with interstellar gas. This mechanism would suggest a direct link between the Fermi bubbles and the population of cosmic rays in the galaxy, providing a valuable testbed for studying these enigmatic particles. Both scenarios are plausible, and ongoing research aims to determine which processes dominate within the bubbles. The discovery of the Fermi bubbles has also spurred new interest in the study of galactic winds, streams of gas and particles that flow outward from a galaxy's core. These winds are thought to be driven by various mechanisms, including supernova explosions, active black holes, and intense star formation. The Fermi bubbles may represent a particularly dramatic example of such a wind, driven by a powerful outburst from Sagittarius A*, or a burst of star formation in the past. Understanding the connection between the bubbles and galactic winds could shed light on how galaxies regulate their growth and evolution. The study of the Fermi bubbles has even extended to other galaxies, as astronomers search for similar structures in the cosmos. While the Fermi bubbles are unique in their size and prominence, other galaxies with active or recently active black holes may also exhibit similar features. For example, observations of nearby galaxies like M87 and Centaurus A have revealed evidence of large-scale structures that could be analogous to the Fermi bubbles. By comparing these systems, scientists can identify common patterns and processes, enriching our understanding of galaxy evolution. Another compelling area of research involves the role of magnetic fields in shaping the Fermi bubbles. Magnetic fields are notoriously difficult to study, but they are crucial for understanding the behavior of charged particles within the bubbles. Recent studies have suggested that the bubbles may be magnetically dominated regions, where magnetic pressure exceeds thermal pressure. If this is the case, the bubbles could serve as natural laboratories for studying the interplay between magnetic fields and high-energy particles, a topic with broad implications for astrophysics. The age of the Fermi bubbles is another puzzle that continues to captivate researchers. Current estimates suggest that the bubbles are millions of years old, but determining their exact age is challenging. One approach involves studying the distribution of gamma-ray emissions within the bubbles, which can provide clues about how they have evolved over time. Another method involves examining the interactions between the bubbles and the surrounding interstellar medium, which may carry signatures of the bubble's formation and expansion history. The symmetry of the Fermi bubbles is another feature that has drawn significant attention. The bubbles extend almost equally above and below the galactic plane, suggesting a highly organized and centralized energy source. This symmetry raises questions about the nature of the event that created the bubbles. If the bubbles were formed by an outburst from Sagittarius A*, the energy release must have been highly isotropic, meaning it was distributed evenly in all directions. Alternatively, if the bubbles were created by a starburst event, the symmetry may reflect the distribution of massive stars in the galactic core. The edges of the Fermi bubbles are particularly fascinating, as they appear to be sharp and well-defined. This suggests that some mechanism is confining the high-energy particles within the bubbles, preventing them from diffusing into the surrounding interstellar medium. One possibility is that shock waves created during the formation of the bubbles compress the surrounding gas, forming a boundary. Another possibility is that magnetic fields are playing a key role, acting like an invisible barrier that traps particles inside the bubbles. Understanding these edge features is critical for unraveling the bubble's formation and evolution. The Fermi bubbles also raise broader questions about the role of feedback processes in galaxy evolution. Feedback refers to the ways in which energy released by stars and black holes influences the surrounding environment. In the case of the Fermi bubbles, the energy released during their formation would have had a profound impact on the Milky Way, heating gas, accelerating cosmic rays, and potentially triggering or suppressing star formation. By studying these feedback effects, scientists can gain insights into the complex interplay between galaxies and their central black holes. The discovery of the Fermi bubbles has opened up a new frontier in high-energy astrophysics, highlighting the importance of multi-wavelength observations. While gamma-ray data from the Fermi telescope has been instrumental in identifying the bubbles, researchers are also using X-ray, radio, and optical observations to study their properties. Each wavelength provides unique information, allowing scientists to build a more complete picture of the bubbles and their origins. As technology continues to advance, the study of the Fermi bubbles is poised to reach new heights. Future space missions and ground-based observatories will provide even more detailed data, enabling researchers to probe the bubbles at unprecedented scales. These efforts will not only shed light on the mysteries of the Fermi bubbles but also deepen our understanding of the processes that shape galaxies and the universe as a whole. The future of research into the Fermi bubbles is tied closely to advancements in both observational technology and theoretical modeling. As our telescopes and instruments improve, we will gain clearer images, more precise data, and new ways of interpreting what we observe. For instance, the development of next-generation gamma-ray observatories, such as the Cherenkov Telescope Array (CTA), will allow scientists to study the Fermi bubbles in much greater detail. These observatories will have improved sensitivity and resolution, enabling researchers to map the fine structure of the bubbles and investigate their gamma-ray emissions with unparalleled clarity. In addition to gamma-ray observations, advances in radio astronomy are expected to play a key role in unraveling the mysteries of the Fermi bubbles. Radio observations can provide crucial information about the magnetic fields within the bubbles, as well as the populations of high-energy electrons responsible for synchrotron radiation. Instruments like the Square Kilometre Array, SK, which will be the world's largest radio telescope, are poised to make significant contributions to our understanding of the bubbles' magnetic properties and their interaction with the surrounding interstellar medium. High-resolution X-ray observatories will also be invaluable in studying the Fermi bubbles. X-rays can reveal details about the hot gas that fills the bubbles, including its temperature, density, and composition. These observations can help scientists identify the processes heating the gas and driving its expansion. Future X-ray missions, such as the Lynx X-ray Observatory, are expected to provide much sharper images and more sensitive measurements, giving us a closer look at the inner workings of these enigmatic structures. Theoretical modeling is another critical area of research. Scientists use computer simulations to test different hypotheses about the formation and evolution of the Fermi bubbles. These simulations incorporate a wide range of physical processes, including fluid dynamics, cosmic ray transport, and magnetic field interactions. By comparing the results of these simulations with observational data, researchers can refine their models and gain deeper insights into the mechanisms driving the bubble's behavior. One promising avenue for theoretical research involves studying the interaction between the Fermi bubbles and the Milky Way's galactic halo. The galactic halo is a diffuse, spherical region of gas, dark matter, and stars that surrounds the main disk of the galaxy. The bubbles extend deep into this halo, and their interaction with the surrounding gas can provide valuable clues about the bubble's origins and impact. For example, the shock waves generated by the bubble's expansion may compress the gas in the halo, creating observable features that can be compared with simulations. Another intriguing question is whether the Fermi bubbles are unique to the Milky Way or if similar structures exist in other galaxies. Observations of nearby galaxies, such as Andromeda and Centaurus A, have revealed large-scale outflows and bubble-like features, suggesting that these phenomena may be common in galaxies with active or recently active black holes. By studying these extragalactic counterparts, scientists can identify universal patterns and processes, helping to place the Fermi bubbles within a broader cosmic context. The study of the Fermi bubbles also has implications for understanding the role of black holes in galaxy evolution. Sagittarius A*, the supermassive black hole at the center of the Milky Way, is relatively quiet compared to the active black holes found in some other galaxies. However, the existence of the Fermi bubbles suggests that Sagittarius A* may have been much more active in the past. This raises important questions about the life cycle of supermassive black holes and their influence on their host galaxies. By studying the Fermi bubbles, scientists can gain insights into the history of Sagittarius A* and its role in shaping the Milky Way. One particularly exciting possibility is that the Fermi bubbles could be linked to episodic outbursts from Sagittarius A*. If the bubbles were formed by a series of smaller, repeated outbursts rather than a single massive event. This could have implications for our understanding of how black holes release energy. It could also help explain why the bubbles have such a distinct and well-defined structure, as each outburst might have contributed to their growth in a controlled and organized manner. The edges of the Fermi bubbles are another area of active research, as they hold key information about the processes that shape these structures. Observations suggest that the edges are sharp and well-defined, with a sudden drop in gamma-ray emissions outside the bubbles. This sharp boundary could be the result of shock waves created during the bubble's formation, which compressed the surrounding gas and created a distinct edge. Alternatively, the edges might be shaped by magnetic fields, which could act as barriers that trap particles inside the bubbles. Understanding these edge features is critical for piecing together the bubble's history and evolution. The role of magnetic fields in the Fermi bubbles is a particularly fascinating topic. Magnetic fields are notoriously difficult to study, but they are crucial for understanding the behavior of high-energy particles within the bubbles. Recent studies suggest that the bubbles may be magnetically dominated regions, where magnetic pressure exceeds thermal pressure. If this is the case, the bubbles could serve as natural laboratories for studying the interplay between magnetic fields and high-energy particles, providing insights into fundamental astrophysical processes. The potential age of the Fermi bubbles is another question that continues to puzzle scientists. Current estimates suggest that the bubbles are between a few million and tens of millions of years old, but determining their exact age is challenging. One way to estimate the age of the bubbles is to study the distribution of gamma-ray emissions within them, which can provide clues about how they have evolved over time. Another approach involves examining the interactions between the bubbles and the surrounding interstellar medium, which may carry signatures of the bubble's formation and expansion history. The symmetry of the Fermi bubbles is another feature that has captured the attention of researchers. The bubbles extend almost equally above and below the galactic plane, suggesting that they were created by a highly organized and centralized energy source. This symmetry raises questions about the nature of the event that formed the bubbles. If the bubbles were created by an outburst from Sagittarius A*, the energy release must have been highly isotropic, meaning it was distributed evenly in all directions. Alternatively, if the bubbles were formed by a burst of star formation, the symmetry may reflect the distribution of massive stars in the galactic core. The discovery of the Fermi bubbles has also prompted researchers to rethink their understanding of the Milky Way's history. The bubbles serve as a kind of fossil record of past events, preserving evidence of energetic processes that occurred millions of years ago. By studying the bubbles, scientists can piece together a timeline of activity in the galactic core, providing a window into the Milky Way's dynamic past. The Fermi bubbles' connection to the dynamic history of the Milky Way has broader implications for our understanding of galaxies as a whole. These enigmatic structures might represent a universal phenomenon that occurs in many, if not all, galaxies with supermassive black holes. Observing and understanding the Fermi bubbles in detail gives us a blueprint to study similar structures in other galactic systems, which could reveal the common processes that govern galaxy formation, evolution, and energy dynamics. An important focus for researchers is how the Fermi bubbles interact with the cosmic rays that pervade our galaxy. Cosmic rays are high-energy particles, primarily protons, that move near the speed of light. These particles originate from various sources, including supernovae, pulsars, and active galactic nuclei, and they play a significant role in shaping the interstellar medium. The Fermi bubbles are thought to be both sources and reservoirs of cosmic rays, with their energetic processes accelerating particles to extremely high speeds. This makes the bubbles a natural laboratory for studying cosmic ray physics, which remains one of the most challenging areas of astrophysics. The acceleration of particles within the Fermi bubbles is closely tied to the shocks and turbulence that arise from their formation. As the bubbles expand, they create shock fronts where the speed of the gas suddenly changes. These shocks can accelerate particles through processes like diffusive shock acceleration, where particles gain energy by bouncing back and forth across the shock front. This process is believed to be responsible for producing many of the high-energy cosmic rays observed in our galaxy. Additionally, turbulence within the bubbles may play a key role in accelerating particles. Turbulence creates chaotic and unpredictable flows of gas, which can transfer energy to particles and boost them to higher speeds. This is similar to the way energy cascades in a turbulent fluid, with larger motions breaking down into smaller, more energetic eddies. Studying these turbulent processes in the Fermi bubbles can help scientists understand how energy is distributed and transferred in astrophysical environments. The study of the Fermi bubbles also intersects with broader questions about the nature of dark matter. Dark matter is a mysterious substance that makes up about 27% of the universe's mass energy content, yet it remains undetectable except through its gravitational effects. Some theories suggest that dark matter particles could annihilate or decay, producing gamma rays as a byproduct. If this is true, the Fermi bubbles could provide a unique opportunity to search for signals of dark matter interactions. By analyzing the gamma-ray emissions from the bubbles, scientists can look for patterns or features that might indicate the presence of dark matter. One of the most intriguing aspects of the Fermi bubbles is their potential role in influencing star formation in the Milky Way. The bubbles are thought to inject large amounts of energy into the surrounding interstellar medium, heating the gas and driving it away from the galactic center. This process, known as feedback, can suppress star formation by preventing gas from cooling and collapsing into new stars. However, feedback can also trigger star formation in certain conditions by compressing gas into dense regions where it can more easily collapse. Understanding how the Fermi bubbles influence star formation is crucial for building a complete picture of the Milky Way's evolution. Another fascinating question is how the Fermi bubbles interact with the magnetic field of the Milky Way. The Milky Way's magnetic field is a complex and poorly understood structure that plays a significant role in shaping the galaxy's dynamics. It influences the motion of charged particles, the behavior of gas clouds, and the propagation of cosmic rays. The Fermi bubbles are thought to be magnetized, and their expansion may have significant effects on the galactic magnetic field. For example, the bubbles could stretch and distort the magnetic field lines, creating complex patterns that affect the motion of particles and the structure of the interstellar medium. One of the major challenges in studying the Fermi bubbles is distinguishing their emissions from those of other sources. The Milky Way's center is a bustling region filled with stars, gas clouds, and energetic phenomena, all of which produce gamma rays. Separating the Fermi bubbles' gamma-ray signal from this background requires sophisticated data analysis techniques and careful modeling. Scientists use statistical methods to identify the distinct spatial and spectral features of the bubbles, allowing them to isolate the bubbles' contributions and study them in detail. The study of the Fermi bubbles also highlights the importance of collaboration in modern astrophysics. Unraveling the mysteries of these structures requires input from a wide range of disciplines, including observational astronomy, theoretical physics, and computational modeling. Teams of scientists work together to collect and analyze data, develop models, and interpret their findings. This collaborative approach has been essential for making progress in understanding the Fermi bubbles and will continue to drive future discoveries. One particularly exciting area of future research involves studying the Fermi bubbles in multiple wavelengths of light. While gamma rays are the most prominent emission from the bubbles, they also emit radiation in other parts of the electromagnetic spectrum, including X-rays, radio waves, and microwaves. Each wavelength provides unique information about the bubble's properties, such as the temperature, density, and composition of the gas. By combining data from multiple wavelengths, scientists can build a more complete picture of the Fermi bubbles and the processes driving their evolution. The Fermi bubbles also have implications for our understanding of galaxy clusters, the largest structures in the universe. Galaxy clusters are massive collections of galaxies bound together by gravity, and they often contain hot, diffuse gas that emits X-rays. Some galaxy clusters show evidence of large-scale bubbles similar to the Fermi bubbles, which are thought to be driven by the activity of supermassive black holes at their centers. Studying the Fermi bubbles in the Milky Way can provide insights into the mechanisms that produce these bubbles in galaxy clusters, helping scientists understand how energy is distributed on cosmic scales. As we continue to study the Fermi bubbles, it is clear that they are not just a local phenomenon, but part of a much larger story about the universe. They serve as a reminder of the immense energy and dynamic processes at work in the cosmos, from the smallest particles to the largest structures. The Fermi bubbles are a testament to the power of observation, curiosity, and collaboration, and they hold the promise of many more discoveries to come. The Fermi bubbles are also a fascinating lens through which to study the interplay between the visible and invisible forces shaping our universe. While their gamma-ray emissions are among the most conspicuous features, the broader processes involved, such as magnetohydrodynamics, particle acceleration, and shockwave formation, require deeper exploration. These dynamics illustrate how energetic phenomena can leave imprints on galactic structures long after their initial events. One of the pressing questions is how the bubbles interact with the Milky Way's vast halo of gas. The galactic halo, an extended, spherical region of tenuous gas enveloping the galaxy, plays a critical role in galactic evolution. The Fermi bubbles extend into this halo, potentially influencing its temperature, density, and motion. Observations suggest that the bubbles could be driving powerful winds into the halo, redistributing gas that might otherwise form stars or fuel the central black hole. These winds could also mix different chemical elements, enriching the halo with materials ejected from the galaxy's core. Interestingly, the Fermi bubbles may also act as cosmic lighthouses, illuminating the structures within the halo. Their gamma-ray emissions interact with the surrounding medium, revealing its composition and dynamics. Scientists use this light to trace the distribution of gas and magnetic fields far beyond the galaxy's visible disk. This process, called light echoing, allows researchers to study regions that are otherwise inaccessible with current technology. The bubbles also offer an opportunity to probe the enigmatic phenomenon of galactic outflows. Galactic outflows are streams of gas and energy that escape from a galaxy's core, often driven by processes like supernova explosions or the activity of a supermassive black hole. These outflows can significantly alter the galaxy's environment, regulating star formation and shaping its structure. The Fermi bubbles are among the most prominent examples of such outflows, and their study provides critical insights into how galaxies regulate themselves over billions of years. Another aspect of the Fermi bubble's significance lies in their symmetry. Unlike many other astrophysical phenomena, which are often chaotic or asymmetric, the Fermi bubbles are strikingly bilaterally symmetric, extending equally above and below the galactic plane. This symmetry is a powerful clue about their origin. It suggests that whatever produced the bubbles was centered in the galactic core and operated in a way that distributed energy evenly in both directions. The leading theory is that the supermassive black hole at the center of the Milky Way, Sagittarius A*, underwent a phase of intense activity, releasing massive amounts of energy that inflated the bubbles. This process, called an active galactic nucleus (AGN) phase, is thought to occur in many galaxies with central black holes. The idea that the Fermi bubbles are remnants of an AGN phase raises intriguing questions about the Milky Way's past. Sagittarius A* is relatively quiet today, but the existence of the Fermi bubbles suggests that it was far more active in the not-too-distant past, possibly a few million years ago. This activity might have been triggered by a large influx of gas or the merger of smaller black holes. Understanding what caused this activity can provide a window into the dynamic history of our galaxy's core. The Fermi bubbles also challenge our understanding of energy transfer on galactic scales. The sheer amount of energy required to create these structures is staggering, equivalent to millions of supernovae exploding simultaneously. This energy would have been released in a relatively short period, possibly less than 1 million years. How this energy was transferred from the black hole to the surrounding gas, and how it managed to create such coherent structures, is still a matter of intense study. Models suggest that jets of plasma, launched at nearly the speed of light, could have funneled the energy into the surrounding medium, inflating the bubbles like a cosmic balloon. Further complicating the picture is the role of turbulence within the bubbles. Turbulence is a chaotic, swirling motion that can transfer energy across different scales. In the Fermi bubbles, turbulence might play a key role in sustaining their structure and accelerating particles. Observing and modeling this turbulence is a major challenge, as it requires advanced simulations and precise measurements of the bubble's properties. The edges of the Fermi bubbles, where their emissions drop off sharply, are particularly interesting. These edges are thought to represent shock fronts, where the fast-moving gas within the bubbles collides with the slower-moving gas in the surrounding medium. These shocks can compress and heat the gas, creating conditions for new physical processes to occur. For example, they might trigger the formation of magnetic fields or generate new populations of high-energy particles. Studying these shock fronts can reveal how energy is dissipated in astrophysical systems and provide clues about the origins of cosmic rays. The Fermi bubbles' ability to influence their surroundings extends to their impact on the Milky Way's spiral arms. The arms of a spiral galaxy like the Milky Way are regions of enhanced star formation, shaped by density waves moving through the galaxy's disk. The Fermi bubbles, with their powerful outflows and energy injections, might interact with these density waves, altering the pattern of star formation in the galaxy. This interplay between the bubbles and the spiral arms is a relatively unexplored area of research, but has the potential to reveal new connections between different components of the galaxy. Another fascinating avenue of study is the Fermi bubbles' potential to produce unique observational signatures in other galaxies. If similar structures exist in other galaxies, they could appear as bright, extended features in gamma-ray or X-ray images. Identifying these features and comparing them to the Fermi bubbles could help scientists understand whether these structures are common and what factors influence their formation and evolution. In the broader context of cosmic evolution, the Fermi bubbles highlight the role of feedback in regulating galaxies. Feedback processes, where energy from stars or black holes affects the surrounding environment, are crucial for understanding why galaxies look the way they do. The Fermi bubbles are a spectacular example of feedback in action, showcasing how a single event can leave an indelible mark on a galaxy's structure and behavior. As our observational capabilities continue to improve, the study of the Fermi bubbles will undoubtedly yield new insights. Upcoming missions like the European Space Agency's Athena X-ray Observatory and the Cherenkov Telescope Array will provide unprecedented views of the high-energy universe, allowing us to study the Fermi bubbles in greater detail. These observations will help answer lingering questions about their origins, dynamics, and interactions with the galaxy. The Fermi bubbles are a reminder of the immense power and complexity of the universe. They represent a chapter in the Milky Way's history that we are only beginning to understand, and their study promises to reshape our understanding of galactic physics, cosmic rays, and the behavior of supermassive black holes. With each new discovery, we come closer to unraveling the mysteries of these enigmatic structures, revealing the hidden forces that shape our galaxy and the universe beyond. The enduring mystery of the Fermi bubbles lies not only in their grandeur but also in the secrets they hold about the forces that govern galaxies like our own. As we delve deeper into their intricate details, it becomes clear that these structures are a window into processes far more profound than their visible glow suggests. From their gamma-ray emissions to their shock fronts and influence on the galactic environment, the Fermi bubbles provide an unparalleled laboratory for studying the complex interplay of energy, matter, and magnetic fields on a galactic scale. One of the most compelling aspects of the Fermi bubbles is their potential to illuminate the cosmic history of our galaxy. The symmetry and scale of these bubbles imply a singular, energetic event in the Milky Way's past, a moment when the galactic core erupted with unimaginable power. This eruption likely propelled jets of plasma at relativistic speeds, carving out the massive cavities that now extend tens of thousands of light-years above and below the galactic plane. These jets may have been fueled by an accretion disk of gas spiraling into the supermassive black hole, releasing gravitational energy as heat and radiation. The study of the Fermi bubbles also underscores the importance of feedback mechanisms in galactic ecosystems. Feedback refers to the ways in which processes like star formation, supernova explosions, and black hole activity regulate the behavior of galaxies. The Fermi bubbles are a striking example of feedback on a grand scale, demonstrating how energy released in the galactic core can propagate outward, influencing the galaxy's structure and dynamics. By examining the Fermi bubbles, researchers gain insights into how similar processes might operate in other galaxies, shaping their evolution over billions of years. The bubbles' sharp edges, often described as their limbs, are particularly intriguing. These regions are thought to mark the boundary where the fast-moving gas within the bubbles meets the surrounding medium. The collisions at these boundaries create shock waves, compressing and heating the gas while generating turbulence. This turbulence plays a crucial role in the bubbles' longevity, helping to sustain their structure against the forces that would otherwise disperse them. Understanding the physics of these shock fronts is essential for unraveling the bubble's origins and evolution. The magnetic fields within the Fermi bubbles are another area of intense study. These fields, which are tangled and amplified by the turbulent motions of the gas, influence the behavior of charged particles and the propagation of gamma rays. Observations suggest that the magnetic fields within the bubbles are surprisingly strong, comparable to those found in the most active regions of star formation. These fields may act as cosmic accelerators, boosting particles to nearly the speed of light and contributing to the production of high-energy gamma rays. The Fermi bubbles' gamma-ray emissions are a treasure trove of information about the extreme conditions within the bubbles. These emissions are thought to result from interactions between high-energy particles, such as electrons and protons, and the surrounding medium. One possible mechanism is inverse Compton scattering, where high-energy electrons collide with low-energy photons, transferring energy to the photons and producing gamma rays. Another possibility is pion decay, where high-energy protons collide with atomic nuclei, producing particles that decay into gamma rays. By analyzing the gamma-ray spectrum of the Fermi bubbles, scientists can infer the energy and distribution of the particles within them. The presence of these high-energy particles also raises questions about their origin. Did they originate from the supermassive black hole's jets, or were they accelerated by shock waves within the bubbles? Answering this question requires a detailed understanding of particle acceleration mechanisms, such as Fermi acceleration, which occurs when particles gain energy by bouncing between shock fronts. These processes are not only relevant for the Fermi bubbles but also for understanding cosmic rays, the mysterious high-energy particles that pervade the universe. In addition to their scientific significance, the Fermi bubbles have sparked curiosity about their potential impact on life within the Milky Way. If the bubbles were created by a past outburst from the supermassive black hole, the resulting radiation could have affected the galaxy's habitability. For example, a powerful gamma-ray burst could have influenced the chemistry of planetary atmospheres or even triggered mass extinctions. While there is no direct evidence linking the Fermi bubbles to such events, their study highlights the interconnectedness of cosmic phenomena and the potential for distant processes to influence life on Earth. The discovery of the Fermi bubbles has also led to a re-evaluation of historical observations. Some researchers have speculated that ancient astronomers may have witnessed the effects of the bubbles' formation, such as unusual patterns of light in the night sky. While these ideas are highly speculative, they illustrate the enduring fascination with the mysteries of the cosmos, and the ways in which modern science can shed light on ancient phenomena. Looking ahead, the future of Fermi bubble research is bright. New observational tools, such as next-generation X-ray and gamma-ray telescopes, will provide unprecedented views of these structures, allowing scientists to probe their properties in greater detail. Advanced simulations, powered by supercomputers, will help researchers model the complex interplay of forces within the bubbles, from the behavior of magnetic fields to the dynamics of particle acceleration. These efforts will not only deepen our understanding of the Fermi bubbles but also advance our knowledge of the broader processes that shape galaxies and the universe as a whole. The Fermi bubbles stand as a testament to the power and complexity of the universe, a vivid reminder that our galaxy is far from static or simple. They challenge our understanding, inspire new questions, and push the boundaries of what we know about the cosmos. As we continue to study these enigmatic structures, we are not just unraveling the story of the Milky Way, we are also exploring the fundamental forces that govern the universe, revealing a cosmos that is as dynamic as it is mysterious. The journey to understand the Fermi bubbles is far from over. Every new observation, every refined model, and every unexpected discovery brings us closer to solving the puzzle of their origins and significance. And as we gaze at these massive structures stretching across the galaxy, we are reminded of the boundless curiosity and ingenuity that drive our exploration of the universe. In the end, the Fermi bubbles are not just a mystery to be solved, they are a gateway to a deeper understanding of our place in the cosmos. As our understanding of the Fermi bubbles evolves, we find ourselves at the intersection of multiple disciplines, astrophysics, cosmology, particle physics, and even the study of galactic evolution. What initially appeared to be an intriguing yet isolated phenomenon is now recognized as a crucial piece of the cosmic puzzle. The Fermi bubbles compel us to reconsider the mechanisms that drive galaxy formation and transformation. They serve as an observational bridge between the theoretical models of galactic feedback and the empirical data we gather from the universe. Understanding the bubble's origins and behavior may unlock a new era of discoveries about how galaxies, including our own Milky Way, evolve over billions of years. The Fermi bubbles also provide a unique opportunity to test the limits of current astrophysical theories. For instance, one of the key aspects of their study is the physics of high-energy processes. Researchers are keen to determine the specific mechanisms responsible for the acceleration of particles to near-light speeds, a process that could potentially alter our understanding of cosmic ray origins. Moreover, the interaction of these accelerated particles with interstellar gas and dust raises further questions about the impact of such high-energy processes on the galactic medium itself. Current models suggest that the central black hole's energy outflows could be responsible for the bubbles, with powerful jets or winds from the supermassive black hole in the galactic center depositing energy into the surrounding interstellar medium. But these jets might not only influence the bubbles, they could also shape the overall structure of the Milky Way. It's possible that the bubbles, in their ongoing evolution, play a significant role in the galactic outflow, impacting star formation and the distribution of gas and dust across the galaxy. This interconnection between the bubbles and galactic dynamics could be pivotal in understanding how the Milky Way has evolved and what may happen to it in the distant future. The science behind the Fermi bubbles is also evolving as new observational technologies come online. The launch of new space telescopes and advancements in ground-based observatories are beginning to offer sharper, more detailed views of the bubbles. Instruments like the Chandra X-ray Observatory and the upcoming James Webb Space Telescope will provide critical data on the temperature, composition, and dynamics of the gases and magnetic fields within and around the Fermi bubbles. These enhanced observations will likely push the boundaries of what we know about these structures, unveiling previously hidden aspects of their nature. In addition to the insights they offer into our own galaxy, the study of the Fermi bubbles is shedding light on other galaxies and the broader universe. The Milky Way is just one example of the many galaxies in the cosmos that could host similar structures. The study of galactic feedback mechanisms, including the formation of bubbles, can help us make predictions about the life cycles of galaxies across the universe. This broader perspective will be essential as we continue to explore distant galaxies, both near and far, and try to understand how they differ from our own. What's also particularly compelling about the Fermi bubbles is how they reveal the intimate connection between observable phenomena and the invisible forces that govern the universe. High-energy particles, magnetic fields, shockwaves, and plasma dynamics are all factors that shape the bubble's structure. Yet, none of these factors are directly observable by the naked eye, nor can they be easily captured by traditional telescopes. It is only through the detection of gamma-ray emissions that we gain insight into this hidden world. The Fermi bubbles, in a sense, are a cosmic fingerprint, marking the area where the observable universe intersects with realms that we can only probe indirectly. By studying these bubbles, scientists are able to refine their understanding of cosmic rays, those mysterious, high-energy particles that streak through space at nearly the speed of light. Cosmic rays are not only one of the most energetic phenomena we know of, but they also offer a glimpse into the mechanisms of particle acceleration at extreme scales. With the Fermi bubbles providing a natural laboratory, researchers can observe how cosmic rays interact with the surrounding interstellar medium, providing valuable clues about the environments that produce these high-energy particles. However, the deeper we delve into the Fermi bubbles, the more questions arise. The precise nature of the energy source driving the bubbles is still a topic of intense debate. Is it truly the supermassive black hole at the center of the galaxy? Or are other processes, like star formation or the death throes of massive stars, contributing to the bubble's creation? The answer may lie in future observations, as astronomers continue to gather data on the behavior of the bubbles and the forces shaping them. Moreover, the alignment and shape of the Fermi bubbles raise further questions. Their symmetry and distinct boundaries suggest a coherent, large-scale event, but the exact cause of such an event is elusive. Was the eruption that created the bubbles a one-time event, or is it part of a recurring cycle? If it is cyclical, how often do such outbursts occur in the history of the galaxy, and what implications does this have for the future of the Milky Way? The role of magnetic fields in the Fermi bubbles is also an open question. Magnetic fields are believed to play a crucial role in the acceleration of particles within the bubbles, but the details of how they shape the dynamics of the structure are still being unraveled. These fields could help explain the strange behavior of the bubble's gamma-ray emissions, and understanding their properties could open up new avenues of research into the nature of magnetic fields in other galaxies. The study of the Fermi bubbles also intersects with the study of other large-scale structures in the universe. For example, the bubble's enormous size, stretching over 50,000 light-years in both directions, places them among the largest known features in the galaxy. Their scale rivals that of galactic clusters, which are vast collections of galaxies bound together by gravity. The Fermi bubbles offer a striking example of how the energetic processes within a single galaxy can lead to the creation of structures on an almost galactic scale. This realization has profound implications for our understanding of the larger forces that govern cosmic evolution. Additionally, as astronomers peer further into the depths of space, the possibility arises that other galaxies may harbor similar structures. In fact, some researchers suspect that such bubbles might be a common feature of many galaxies with supermassive black holes at their centers. If this is the case, the Fermi bubbles may be just one example of a broader cosmic phenomenon. Investigating these structures in other galaxies will be an exciting next step in unraveling the mysteries of galactic feedback processes and their role in shaping the evolution of galaxies across the universe. As we look forward to the future of Fermi bubble research, the potential for discovery is immense. With upcoming advancements in observational technology, including the launch of next-generation space telescopes and the continued improvement of ground-based observatories, we can expect a wealth of new data on these enigmatic structures. As researchers refine their models and techniques, the Fermi bubbles will undoubtedly continue to be a focal point for astrophysicists and cosmologists alike. The Fermi bubbles are much more than just intriguing structures. They are a testament to the power and mystery of the universe. By studying them, we not only gain insights into the workings of our own galaxy but also broaden our understanding of the cosmos as a whole. The Fermi bubbles are a cosmic enigma, offering a glimpse into the forces that shape galaxies and the universe itself. As we continue to explore their origins and dynamics, we are not only uncovering the secrets of the Milky Way but also advancing our understanding of the very fabric of space and time. As our understanding of the Fermi bubbles continues to evolve, one of the most exciting possibilities is that their study could offer key insights into the fundamental nature of cosmic energy. The processes that drive the bubbles could be tied to the mechanics of dark matter or dark energy, two of the most perplexing and elusive components of the universe. By exploring the Fermi bubbles, scientists may inadvertently uncover clues about the forces that are believed to make up the vast majority of the universe's mass and energy, yet remain invisible and undetectable through traditional means. These bubbles could also provide a unique window into the workings of the supermassive black hole at the center of the Milky Way. As astronomers observe the bubbles' emissions and their surrounding structures, they are not just studying the gas and dust that make up these regions but also the incredibly powerful gravitational forces that shape the very heart of our galaxy. Supermassive black holes, like the one in our galaxy, have long been the subject of fascination due to their ability to warp space and time in profound ways. The Fermi bubbles may be just one of many ways that these mysterious objects impact their environments, though we are still far from understanding the full extent of their influence. While the current focus is on the origin of the bubbles, the study of these structures also brings up questions about their long-term fate. Just as the formation of the bubbles was likely a dramatic event, their eventual evolution and eventual dissipation are topics of great interest. What happens when these massive outflows of energy reach the outer limits of the galaxy's influence? Do they simply dissipate into the vast expanse of intergalactic space, or do they interact with the larger structures of the universe in some meaningful way? This could lead us to consider the broader implications for the future of the Milky Way. If these energy-driven processes, such as the formation of the Fermi bubbles, are a natural part of a galaxy's life cycle, could they offer clues about the ultimate fate of our galaxy? As we look billions of years into the future, we may find that the Milky Way's dynamic environment is constantly evolving, shaped by events like the Fermi bubbles that reflect the inner workings of our galaxy's heart. Beyond the Milky Way, the Fermi bubbles could have far-reaching implications for the study of galaxy formation and evolution. Although we can't directly observe the centers of other galaxies with the same detail that we observe our own, the principles behind the creation and behavior of the Fermi bubbles may be applicable across many galaxies. Similar energy outflows, potentially in the form of massive jets or bubbles, could be present in other galactic centers. Observing these events in distant galaxies will help us piece together a much larger narrative about the forces that govern galaxy life cycles, from birth to death and everything in between. Another captivating aspect of the Fermi bubbles is their role in regulating the galactic ecosystem. Galaxies are dynamic entities, constantly evolving and interacting with their surroundings. The outflows generated by the Fermi bubbles could play a crucial role in regulating star formation within the galaxy. When the bubbles expel energy, they push out gas and dust, reducing the material available to form new stars. In this sense, the Fermi bubbles might serve as a cosmic thermostat, controlling the rate at which new stars are born and influencing the long-term evolution of the galaxy. This feedback mechanism is part of a broader class of galactic processes known as feedback loops. These loops are responsible for shaping the overall structure of a galaxy over time, and understanding the nature of the Fermi bubbles could offer new insights into how feedback processes work in galaxies of all sizes. The interplay between star formation, black hole activity, and the galactic medium is an area of active research, and the Fermi bubbles represent a crucial piece of the puzzle. The discovery of the Fermi bubbles is also a reminder of how much remains to be discovered in the universe. Despite the incredible advances in technology and our growing understanding of the cosmos, the Milky Way is still full of mysteries. Each new discovery, whether it's the Fermi bubbles, gravitational waves, or exoplanets, opens up even more questions that we can't yet fully answer. And it is through this continuous process of discovery, questioning, and rethinking our assumptions that we are able to unlock the deeper secrets of the universe. While the science of the Fermi bubbles is still in its early stages, the implications for future research are vast. Astronomers and physicists are already using the bubbles to probe the behavior of high-energy particles, the dynamics of galactic winds, and the interplay between black holes and their surrounding environments. As we gather more data from increasingly advanced instruments, the Fermi bubbles could become one of the defining features in our understanding of how galaxies evolve. In the broader context of space exploration, the Fermi bubbles also highlight the importance of gamma-ray astronomy. This relatively young field is helping to reveal the universe in ways that optical telescopes simply cannot. By detecting high-energy photons, gamma rays, astronomers are able to observe some of the most extreme environments in the universe, such as the centers of galaxies, black holes, and supernovae remnants. The study of the Fermi bubbles is just one example of how gamma-ray astronomy can provide new insights into the complex and energetic processes that shape the cosmos. In the years to come, we can expect even more detailed observations of the Fermi bubbles, as new space missions and observatories come online. The upcoming James Webb Space Telescope, for example, promises to revolutionize our understanding of the universe across a wide range of wavelengths. By studying the Fermi bubbles through a variety of observational tools, we can continue to refine our models and theories, gradually uncovering the true nature of these fascinating structures. Ultimately, the study of the Fermi bubbles represents a small but crucial step in our ongoing exploration of the cosmos. As we continue to investigate the origins and behavior of these enigmatic structures, we may unlock some of the deepest mysteries of our galaxy and beyond. In doing so, we will not only learn more about the Milky Way's past and future but also gain a greater understanding of the fundamental forces that shape all galaxies across the universe. As we peer deeper into the unknown, the Fermi bubbles stand as a symbol of the boundless curiosity that drives humanity to explore the farthest reaches of space. While the bubbles themselves may one day dissipate, their legacy will continue to inspire future generations of astronomers and astrophysicists. And as long as we continue to ask the big questions and search for the answers, the mysteries of the universe, like the Fermi bubbles, will remain a testament to our quest for knowledge. As our research into the Fermi bubbles deepens, one of the most intriguing aspects is the role they play in shaping the larger-scale environment of the Milky Way. While the bubbles themselves are vast structures that emit high-energy gamma rays, they are also part of a more intricate cosmic dance involving the supermassive black hole at the galactic center, the interstellar medium, and the complex feedback mechanisms that drive the evolution of the galaxy. These cosmic features are all interconnected, and by studying the Fermi bubbles, we gain valuable insight into the processes that govern the behavior of our galaxy. One of the most important questions is how the bubbles are formed. While there is no definitive answer yet, many theories suggest that the outflows are connected to the activity of the supermassive black hole, Sagittarius A star. This black hole, which lies at the very center of our galaxy, is surrounded by a dense cluster of stars and gas. The black hole itself is not static. Rather, it is thought to be constantly accreting matter from its surroundings, a process that generates immense energy. Some of this energy is expelled in the form of high-energy jets, which could explain the formation of the Fermi bubbles. These jets, or outflows, might be expelled perpendicular to the plane of the Milky Way, producing the observed bubbles that extend above and below the galactic core. But what exactly drives these outflows? Some scientists believe that the bubbles are a result of a catastrophic event, such as a sudden increase in the black hole's accretion rate. This could happen if a massive cloud of gas or a star were to fall into the black hole, causing a sudden surge of energy. Other theories suggest that the bubbles might be the result of more continuous processes, like the slow and steady feeding of the black hole over millions of years. Whatever the cause, the outflows of energy and matter from the black hole are likely to have far-reaching consequences for the surrounding galaxy. While the Fermi bubbles themselves are fascinating objects to study, they are also a window into the larger processes that govern the structure and evolution of galaxies. In particular, their study can shed light on the phenomenon of galactic feedback. This refers to the way in which the energy and matter produced by a galaxy's central black hole can influence the surrounding galaxy, regulating star formation and the overall growth of the galaxy. In the case of the Milky Way, the Fermi bubbles may be one of the most significant manifestations of this feedback process, driving the outflow of gas and dust that can suppress the formation of new stars. But the feedback process doesn't end with the bubbles. As the energy from the bubbles interacts with the surrounding interstellar medium, it may trigger the formation of new structures, such as supernova remnants and stellar nurseries. These structures, in turn, contribute to the ongoing evolution of the galaxy. In this way, the Fermi bubbles are not just passive observers of the galactic landscape, they are active participants in shaping the future of the Milky Way. As scientists continue to study the Fermi bubbles, one of the most important tools in their arsenal is computer modeling. By simulating the behavior of the bubbles and the surrounding gas, astronomers can test different theories about their origin and evolution. These models can also help predict the long-term behavior of the bubbles, providing insights into how they might dissipate over time. In addition to computer simulations, scientists are using a variety of observational techniques to study the bubbles in more detail. From X-ray telescopes to radio observatories, these instruments provide a wealth of data that is helping to refine our understanding of the Fermi bubbles and their place in the cosmos. But there is still much we don't know about the Fermi bubbles. For instance, one of the most perplexing aspects of these structures is the way in which they emit gamma rays. Gamma rays are the highest energy form of light, and their presence in the Fermi bubbles suggests that the bubbles are not only vast but also incredibly energetic. What's more, the distribution of these gamma rays is not uniform. Instead, they seem to be concentrated in certain regions of the bubbles, with some areas emitting far more energy than others. This could indicate the presence of high-energy particles, such as cosmic rays, which are accelerated by the forces at work in the bubbles. Understanding the exact mechanisms behind this gamma-ray emission is a key goal of current research. Another mystery surrounding the Fermi bubbles is their unusual shape. While many galaxies exhibit some form of outflow, few display the symmetrical, lobe-like structure seen in the Milky Way. The fact that the bubbles are so well defined suggests that they are the result of a highly coordinated event, rather than a random or chaotic process. Some scientists believe that the shape of the bubbles could provide clues about the orientation of the black hole's jets, or the dynamics of the gas and dust in the galactic center. Understanding the geometry of the bubbles could also help us learn more about the larger-scale structure of the Milky Way, as well as the behavior of other galaxies. As we look to the future, the study of the Fermi bubbles promises to reveal even more about the hidden processes at work in the Milky Way. With new observational tools and advanced modeling techniques, astronomers will continue to probe the bubbles in greater detail, uncovering the secrets of their formation, energy emission, and role in galactic evolution. Moreover, as we begin to explore other galaxies in greater detail, we may find that the Fermi bubbles are not unique to the Milky Way. Other galaxies, particularly those with active supermassive black holes, may exhibit similar structures, offering new insights into the commonalities and differences between galaxies across the universe. The discovery of the Fermi bubbles has already had a profound impact on our understanding of the Milky Way, but this is just the beginning. As we continue to explore these enigmatic structures, we are bound to uncover even more surprising revelations about the nature of our galaxy and the forces that shape it. From the high-energy jets of supermassive black holes to the cosmic winds that regulate star formation, the study of the Fermi bubbles provides a rare and exciting glimpse into the dynamic processes that drive the evolution of galaxies. The Fermi bubbles serve as a reminder of how much there still is to learn about the universe. Every new discovery opens up new questions and challenges our assumptions about the cosmos. And as long as we continue to look to the stars and ask the big questions, there will always be mysteries waiting to be uncovered, just like the Fermi bubbles themselves. The importance of the Fermi bubbles extends far beyond just understanding the Milky Way. These massive gamma-ray-emitting structures offer insights into the high-energy processes that occur at the hearts of galaxies, particularly around supermassive black holes. They raise important questions about how galaxies evolve, how matter and energy interact on an enormous scale, and how feedback mechanisms regulate the star formation that is critical to a galaxy's growth. In some ways, the Fermi bubbles have become a cosmic puzzle, with pieces scattered across different research fields in astrophysics, and researchers are eager to connect them. In particular, the ongoing study of the bubbles can help answer fundamental questions about the role of black holes in galaxy formation. This is crucial because supermassive black holes are believed to be present at the center of most galaxies, and they play a central role in shaping their environments. The outflows produced by these black holes, which may manifest as the Fermi bubbles, could be a key factor in determining whether a galaxy undergoes sustained star formation or becomes quiescent and ceases to form new stars. The feedback from black holes could also play a significant role in regulating the interstellar medium, the gas and dust that fills the space between stars. The Fermi bubbles represent a perfect laboratory for studying how high-energy phenomena like supermassive black hole outflows influence the surrounding gas, shaping the conditions under which stars can be born. For example, the energy expelled by the bubbles could heat the surrounding gas, preventing it from cooling and collapsing to form new stars. This could explain why some regions of galaxies, including the center of the Milky Way, exhibit little star formation despite the presence of abundant gas. Another interesting aspect of the Fermi bubbles is their connection to cosmic rays. The bubbles are thought to contain high-energy particles that have been accelerated to nearly the speed of light. These cosmic rays are one of the most mysterious and energetic phenomena in the universe, and their study could provide key insights into the processes that occur around supermassive black holes. Some scientists believe that the Fermi bubbles could be a source of cosmic ray acceleration, with the energy from the black hole's outflows creating the conditions necessary for these particles to gain incredible speeds. But what exactly are cosmic rays, and why are they so important? Cosmic rays are high-energy particles, primarily protons, that travel through space at nearly the speed of light. When they interact with matter, they can produce a variety of other particles, including gamma rays. This is why the Fermi bubbles, which emit gamma rays, are so closely tied to the study of cosmic rays. By understanding how cosmic rays are produced and accelerated in regions like the Fermi bubbles, scientists can gain a deeper understanding of the fundamental physics of particle acceleration and how it operates in extreme environments. Interestingly, the Fermi bubbles also shed light on the broader universe. Although they are unique in many respects, the processes that give rise to the Fermi bubbles are not exclusive to the Milky Way. Other galaxies, especially those with active supermassive black holes, may exhibit similar outflows, and the study of these bubbles can help us understand the universal processes at work in galaxies across the cosmos. In fact, astronomers have observed similar bubble-like structures in other galaxies, suggesting that the Fermi bubbles may be part of a more common galactic phenomenon. If this is true, then the study of the Fermi bubbles could help unravel some of the broader mysteries of galactic evolution and feedback mechanisms that shape the universe. As our ability to observe the universe improves, particularly with next-generation telescopes and space-based observatories, we will be able to gather more detailed data on the Fermi bubbles and other similar structures. Instruments like the James Webb Space Telescope, the upcoming Nancy Grace Roman Space Telescope, and more advanced gamma-ray observatories will provide astronomers with the tools they need to peer deeper into the cosmos. These observations will likely offer new insights into the composition, structure, and behavior of the Fermi bubbles, and they will help us refine our models of the processes that shape galaxies and black holes. The more we learn about the Fermi bubbles, the more we realize how little we actually know. For example, one of the biggest unknowns is the exact composition of the bubbles. Although they emit gamma rays, the specific elements and particles that make up the bubbles are still largely a mystery. Are they made entirely of gas, or do they contain other forms of matter? Are they simply a result of energetic outflows from the black hole, or do they also interact with the surrounding galactic environment in more complex ways? These are questions that researchers are actively working to answer, and new discoveries about the composition of the bubbles could unlock even more profound insights into the physics of the universe. Another ongoing mystery is the nature of the boundary between the Fermi bubbles and the surrounding galactic environment. The bubbles appear to be expanding outward from the galactic center, but their edges are not perfectly defined. Instead, they seem to diffuse gradually into the surrounding gas, making it difficult to pinpoint exactly where the bubbles end and the rest of the galaxy begins. This raises important questions about the physical processes that govern the dynamics of such large-scale outflows. Do the bubbles eventually dissipate into the surrounding medium, or do they somehow continue to evolve over time? How do they interact with the interstellar gas and dust, and how do they influence the larger-scale structure of the Milky Way? Even though the Fermi bubbles remain one of the most enigmatic features of our galaxy, their study has already led to important breakthroughs in astrophysics. The bubbles are a rare and unique phenomenon, and their investigation has yielded insights into the dynamics of active galactic nuclei, the nature of black hole feedback, and the processes that govern galaxy evolution. By continuing to study these mysterious structures, we are not only learning more about the Milky Way but also uncovering universal principles that apply to galaxies throughout the universe. The Fermi bubbles are, in a sense, a testament to the power of discovery. They are the result of a combination of cutting-edge technology, serendipitous observations, and the curiosity that drives us to explore the unknown. As astronomers and astrophysicists continue to study the bubbles, the Milky Way will reveal more of its secrets that could change our understanding of the universe forever. The Fermi bubbles are not just a curiosity, they are a glimpse into the deep, hidden workings of the cosmos. And as we continue to unravel their mysteries, we move one step closer to answering some of the biggest questions in modern science. The story of the Fermi bubbles is still being written. With each new discovery, we uncover more about these fascinating structures and their role in the grander scheme of galactic evolution. And as we push the boundaries of our knowledge, the Fermi bubbles will continue to inspire wonder and curiosity, reminding us of the vast and mysterious universe we are only beginning to understand. The journey of discovery surrounding the Fermi bubbles is far from over. As scientists and astronomers continue their work, they are uncovering new ways to probe these enormous structures, pushing the limits of observational technology and theoretical models. It's crucial to remember that the Milky Way, our home galaxy, is just one part of a much larger and dynamic universe, and every breakthrough related to the Fermi bubbles expands our understanding not just of our galaxy, but of galaxies everywhere. It also opens new avenues of research into the fundamental forces that govern the cosmos. The Fermi bubbles are often discussed in terms of their cosmic significance, how they help us understand the nature of black holes, star formation, and even the dark matter that makes up the bulk of the universe's mass. Yet, it's easy to overlook the way in which they bridge multiple domains of science. Not only do they provide valuable insights into astrophysics, but they also contribute to particle physics, cosmology, and the study of high-energy phenomena. In a way, the study of the Fermi bubbles is an exercise in the interconnectedness of different scientific fields. Understanding how these structures form, evolve, and interact with their environments is an inherently multidisciplinary challenge, requiring expertise in everything from quantum mechanics to the general theory of relativity. While the Fermi bubbles are most famous for their gamma-ray emission, they are not simply hot spots of radiation. Over the years, a growing body of research has focused on uncovering the magnetic fields that permeate these structures. Understanding the nature of these magnetic fields is crucial for several reasons. First, magnetic fields can influence the behavior of charged particles, such as cosmic rays, and understanding them can provide deeper insights into how these high-energy particles are accelerated. Second, these magnetic fields can also affect the propagation of gamma rays, which could help explain the observed characteristics of the Fermi bubbles, such as their size, shape, and emission patterns. The connection between magnetic fields and particle acceleration in the Fermi bubbles has led to some truly fascinating discoveries. Researchers have found that these bubbles may contain highly structured magnetic fields, which could play a significant role in channeling the flow of charged particles. In many ways, the magnetic field acts as a kind of cosmic conduit, directing the path of energetic particles and influencing their interactions with other elements in the surrounding space. For instance, it's possible that these magnetic fields could help explain the observed acceleration of cosmic rays within the bubbles. Some scientists have even suggested that these magnetic fields could be responsible for confining the energy produced by the supermassive black hole, keeping it from dissipating too quickly into space. Another critical aspect of the Fermi bubbles is the feedback loop they represent between the black hole at the center of the Milky Way and the surrounding interstellar medium. The black hole's energetic outflows, seen in the form of high-energy particles, radiation, and even relativistic jets, don't just disappear into space. Instead, they interact with the surrounding gas and dust, creating a feedback mechanism that can either promote or inhibit star formation. The Fermi bubbles may be one of the most direct ways in which this feedback manifests. The energy and particles emitted by the bubbles can heat up the surrounding gas, making it less likely for that gas to collapse and form new stars. This feedback mechanism has broad implications for our understanding of galaxy evolution. In some galaxies, supermassive black holes are thought to regulate the rate at which stars form, with the feedback from the black hole either promoting or suppressing the formation of new stars. The Fermi bubbles could provide us with a window into this complex process. By observing the interaction between the bubbles and the surrounding galactic material, scientists can develop more refined models of how galaxies evolve over time, how stars are born, and how the central black hole influences the overall dynamics of the galaxy. On a grander scale, the Fermi bubbles also highlight the challenges and limitations of our current observational tools. While the discovery of these structures was groundbreaking, it also revealed the gaps in our understanding of the universe. For example, despite their prominence in the sky, the Fermi bubbles have a relatively subtle signature when observed in visible light. It is only through the detection of gamma rays that their true nature is revealed, underscoring the importance of observing the universe across multiple wavelengths. The Fermi bubbles are a reminder of the many hidden wonders in the cosmos, phenomena that are only detectable by peering into the universe using the full spectrum of electromagnetic radiation. As a result, astronomers have turned to a variety of sophisticated instruments to study the Fermi bubbles in greater detail. The Fermi Gamma-ray Space Telescope, for example, is an essential tool in the study of these enigmatic structures. Launched in 2008, this telescope has been at the forefront of gamma-ray astronomy, providing critical data that has allowed researchers to map the bubbles and study their properties. The wealth of information gathered by the Fermi Space Telescope has led to new hypotheses about the formation and evolution of the bubbles, as well as their relationship with other high-energy phenomena in the galaxy. The future of Fermi bubble research looks incredibly promising. With the advent of more advanced observatories and instruments, including the upcoming next-generation space telescopes, researchers are poised to make even more exciting discoveries. The James Webb Space Telescope, for example, is set to revolutionize our understanding of the universe by providing unprecedented resolution in the infrared spectrum. While its primary mission is to study distant galaxies and the formation of stars, its capabilities could also help us learn more about the processes at work in the centers of galaxies, including the supermassive black hole at the heart of the Milky Way. As technology improves, so too will our ability to observe and understand the Fermi bubbles, and we may one day uncover their secrets in ways we never thought possible. Despite the immense challenges of studying these vast cosmic structures, each new discovery brings us closer to understanding not just the Fermi bubbles, but the larger forces that shape our universe. These bubbles offer a glimpse into the extraordinary, high-energy processes that govern the behavior of galaxies and the supermassive black holes at their cores. They serve as a reminder of the mysteries still awaiting us in the vastness of space and the complex interplay between the forces that govern the cosmos. Ultimately, the Fermi bubbles represent an exciting frontier in the study of astrophysics, one that could offer profound insights into the fundamental workings of the universe. They are not just a curiosity of our galaxy but a key piece of the puzzle that could help us unlock many of the mysteries of the cosmos. As we continue to explore and study these enigmatic structures, we will undoubtedly uncover new truths about the nature of space, time, and the universe itself. As we continue to delve deeper into the mysteries of the Fermi bubbles, we're also confronting the limits of our current understanding of cosmic phenomena. The Fermi bubbles stand as a reminder of the complexity of the universe, demonstrating that even within our own galaxy, there are phenomena that are both breathtakingly large and almost impossibly complex. While we've made incredible strides in understanding their general structure and possible origins, there's still much to learn about the subtle details that define them. One of the key areas where researchers are focusing their attention is the internal structure of the Fermi bubbles. Although we know that they extend tens of thousands of light-years above and below the plane of the Milky Way, the precise mechanisms driving the formation and evolution of these vast structures remain elusive. Some theories suggest that the bubbles are the result of violent outflows from the supermassive black hole at the center of the galaxy, known as Sagittarius A star. These outflows, propelled by the gravitational energy of the black hole, may have been released in bursts over millions of years. Other hypotheses propose that the bubbles are formed by the accumulation of material ejected by massive stars and stellar remnants in the galaxy's central regions. Another intriguing avenue of research is the possibility that the Fermi bubbles are connected to a much larger, galactic-scale phenomenon. The idea that the bubbles might be the visible manifestation of a much broader, more diffuse outflow of energy and material is one that has gained traction in recent years. If true, it could mean that the Fermi bubbles are not just an isolated feature of the Milky Way, but part of a more complex, large-scale process that is happening across the galaxy. This would have profound implications for our understanding of galaxy evolution, especially in terms of how galaxies interact with their central black holes and how energy is distributed throughout the galactic environment. Research has also raised the possibility that the Fermi bubbles could be part of a more generalized galactic feedback loop. This feedback loop, which is driven by the intense energy and material flows from the supermassive black hole, could have a cascading effect on the star-forming processes of the galaxy. If the energy released by the bubbles is enough to heat the surrounding gas, it may prevent that gas from cooling and condensing into new stars. This process of suppression of star formation is a critical component of understanding how galaxies evolve over time. On a broader scale, the Fermi bubbles have sparked a renewed interest in the role of supermassive black holes in the universe. For many years, black holes were primarily viewed as objects of immense gravitational power that were capable of swallowing stars and entire planets. However, the discovery of structures like the Fermi bubbles has highlighted the more dynamic role that black holes can play in the shaping of their galaxies. The outflows produced by these black holes may not only regulate star formation, but they could also influence the growth and evolution of the galaxy itself, shaping the distribution of matter and energy in ways that we are only beginning to understand. To further our understanding of the Fermi bubbles, scientists are relying on a combination of observational techniques and cutting-edge technologies. For example, the use of high-resolution gamma-ray telescopes, such as the Fermi Gamma-ray Space Telescope, has provided crucial data that allow researchers to map the extent and intensity of the bubbles. However, in order to unlock the deeper mysteries of these structures, astronomers are also turning to new tools that can detect other forms of radiation, such as X-rays, radio waves, and even gravitational waves. By combining data from multiple sources, scientists can paint a more comprehensive picture of the processes at work within the Fermi bubbles, gaining insights that would be impossible with any single method of observation. Additionally, researchers are using simulations and computer models to test the various hypotheses about the formation and behavior of the Fermi bubbles. These simulations take into account everything from the properties of the supermassive black hole at the galaxy's center to the distribution of gas and dust in the galaxy's plane. By running these models, scientists can compare the predicted behavior of the bubbles with the observations made by telescopes. This process is helping to refine our understanding of the Fermi bubbles, allowing scientists to rule out certain theories and narrow down the possible explanations. One of the most exciting aspects of studying the Fermi bubbles is the potential for future discoveries that could change our fundamental understanding of the universe. As technology improves and our observational capabilities grow, we may uncover new features within the bubbles that we had never even considered. For example, some researchers have suggested that the Fermi bubbles might be home to rare, high-energy phenomena that have never been observed before, such as exotic particles or unusual magnetic fields. If these phenomena are confirmed, they could lead to new breakthroughs in physics, particle theory, and even our understanding of the fundamental forces that shape the universe. Moreover, the study of the Fermi bubbles might reveal new insights into the relationship between galaxies and the supermassive black holes at their centers. It is already known that these black holes play a critical role in the evolution of galaxies, but the exact nature of this relationship remains an open question. The Fermi bubbles, as a direct consequence of the black hole's activity, could offer valuable clues about how galaxies grow and evolve over time. By studying these bubbles in detail, astronomers may be able to better understand how the feedback from black holes influences the structure and behavior of galaxies, both near and far. Another exciting possibility is that the Fermi bubbles could provide a new way of studying dark matter, one of the most mysterious and elusive components of the universe. Dark matter makes up a significant portion of the total mass of the universe, yet it remains invisible to our current instruments. Some scientists have hypothesized that the high-energy radiation emitted by the Fermi bubbles could contain subtle traces of dark matter interactions. By analyzing the gamma-ray spectrum of the bubbles, researchers may be able to detect faint signals that point to the presence of dark matter. This would be a groundbreaking discovery, as it would not only confirm the existence of dark matter but also provide us with a new tool to study its properties and interactions. While the Fermi bubbles are a relatively recent discovery, their study has already made a profound impact on our understanding of the universe. The mysteries surrounding these structures have prompted researchers to rethink many of the ideas that have shaped our understanding of galaxies, black holes, and cosmic phenomena. As we continue to probe the depths of the Fermi bubbles and uncover new information, it is clear that they will play a key role in shaping the future of astrophysics and cosmology. The journey of discovery is far from over, and with each new piece of information, we are one step closer to unlocking the secrets of these enigmatic structures and the cosmic forces that drive them. As we look forward to future discoveries, the potential of the Fermi bubbles to revolutionize our understanding of the universe only grows. These structures are not isolated phenomena but rather key pieces of the puzzle that could illuminate the hidden workings of the cosmos. In many ways, the Fermi bubbles represent a crossroad where the boundaries of astronomy, astrophysics, and cosmology intersect. The more we learn about them, the more questions arise, creating an exciting prospect for future research. One of the most significant aspects of the Fermi bubbles is the potential they hold for understanding the connection between large-scale cosmic structures. The bubbles themselves are a product of the interaction between a supermassive black hole and its surrounding environment, which includes not only the gas and dust of the galaxy but also the gravitational forces exerted by other structures in the universe. As we gather more data about the Fermi bubbles, we may begin to see a clearer picture of how black holes, stars, galaxies, and dark matter interact in the vast expanse of space. We might also learn more about the process of galaxy evolution itself. It is theorized that galaxies evolve through a combination of internal processes and external influences. The Fermi bubbles, as part of the energetic outflows from a supermassive black hole, may provide clues about how energy is redistributed throughout a galaxy. This redistribution of energy could play a major role in determining the rate at which stars form, how the gas within a galaxy behaves, and even the fate of galaxies over long periods of time. These outflows may not only be destructive, but could also serve as mechanisms for regulating star formation, potentially preventing certain areas of a galaxy from becoming too crowded with stars while allowing others to form new stars at a healthy pace. Furthermore, the study of the Fermi bubbles has profound implications for understanding the role of supermassive black holes in the larger cosmic ecosystem. Traditionally, black holes have been viewed as cosmic vacuum cleaners, pulling in everything around them and accumulating mass. However, the discovery of structures like the Fermi bubbles challenges this perception, highlighting the active and energetic role that black holes play in their surrounding environments. These outflows from supermassive black holes could help regulate not only the galaxy's structure but its overall behavior, shaping the gas dynamics, star formation, and even the dark matter distribution in the region. An intriguing possibility raised by some researchers is that the Fermi bubbles could be connected to the much larger phenomenon of galactic winds. These galactic winds, which are streams of gas and energy expelled from galaxies, could be powered by the same processes that drive the Fermi bubbles. If this connection is proven to be true, it could have far-reaching consequences for how we view the life cycle of galaxies. These galactic winds may carry energy and material out of galaxies, influencing the growth and evolution of not only the host galaxy but also the surrounding intergalactic medium. The discovery of the relationship between galactic winds and the Fermi bubbles would open up new avenues for studying the dynamic nature of galaxies and the large-scale processes that shape the universe. At the same time, the Fermi bubbles continue to challenge our understanding of energy production on the largest scales. These bubbles are not just clouds of gas. They are energetic powerhouses, releasing immense amounts of gamma radiation that seem to defy our traditional models of energy distribution in the cosmos. The high-energy particles within the bubbles provide insight into the mechanisms of particle acceleration, offering clues about how particles are energized to such extreme levels. This has led to the exploration of new physical phenomena, such as the interaction between magnetic fields and energetic particles, as well as the potential role of exotic particles or dark matter in the process. Looking to the future, one of the most exciting possibilities is the advancement of observational technologies that will allow us to peer even deeper into the heart of the Fermi bubbles. The data collected by current instruments, such as the Fermi Gamma-ray Space Telescope, have already provided invaluable insights into the structure of the bubbles, but the next generation of space telescopes and observatories could push the boundaries of our knowledge even further. Instruments that can observe the universe across a wider range of wavelengths, from X-rays to radio waves, will provide a more comprehensive understanding of the bubbles and the processes that give rise to them. In particular, the use of next-generation radio telescopes like the Square Kilometre Array (SKA) could yield unprecedented data on the interaction between the Fermi bubbles and the intergalactic medium. By detecting radio waves emitted from the bubbles, researchers can gain further insight into their internal structure, the nature of their magnetic fields, and the high-energy processes that power them. Similarly, the development of more sensitive X-ray telescopes could help us detect high-energy emissions from the region surrounding the supermassive black hole at the center of the galaxy, further refining our understanding of the forces at work within the Milky Way's core. The potential for new discoveries doesn't end there. Scientists are also exploring the possibility that the Fermi bubbles could provide a glimpse into the fundamental nature of spacetime itself. Some researchers have proposed that the high-energy radiation emitted by the bubbles might contain information about the structure of spacetime, potentially allowing us to test theories of quantum gravity and the behavior of spacetime at the smallest scales. This could lead to a deeper understanding of the fundamental laws of physics, and could even have implications for our understanding of dark energy and dark matter. As the field of astrophysics continues to evolve, it is clear that the Fermi bubbles will remain a focal point for scientific inquiry. With each new discovery, we move one step closer to unraveling the mysteries of these enigmatic structures and the processes that shape them. In the coming years, we can expect further breakthroughs in our understanding of the Fermi bubbles, and as technology advances, the ability to probe deeper into their structure and origins will open new doors to understanding the complex workings of the Milky Way and the universe as a whole. The study of the Fermi bubbles is not just about answering questions specific to the Milky Way. It is about expanding the horizons of our knowledge and pushing the limits of what we can comprehend about the cosmos. With every piece of data we collect, we gain a clearer picture of how galaxies evolve, how black holes shape their surroundings, and how the universe itself operates on the largest and most energetic scales. The future of space exploration is full of endless possibilities, and the Fermi bubbles will undoubtedly continue to be a key player in unlocking the mysteries of the universe. The implications of the Fermi bubbles extend far beyond our own galaxy, the Milky Way. As astronomers look at similar structures in other galaxies, the potential for understanding galactic phenomena on a broader scale grows. The discovery of similar bubbles in distant galaxies could provide evidence that supermassive black holes play a key role in shaping the evolution of galaxies across the universe. This could reshape our understanding of galaxy formation and evolution and lead to a more comprehensive theory of how black holes, gas dynamics, and star formation interact on the cosmic scale. These large-scale phenomena could also help bridge the gap between local and distant galaxies. The Fermi bubbles provide an excellent example of how we can learn about the distant past and future of galaxies by studying the energetic outflows from supermassive black holes. By comparing the properties of these bubbles across different galaxies, we can develop a more unified theory about the forces that drive galaxy formation and how these forces vary across different regions of the universe. This comparative approach is key to understanding the true nature of the cosmos and its various structures, from the tiniest particles to the largest galaxies. One of the most fascinating aspects of the Fermi bubbles is their relationship with the surrounding intergalactic medium. This is the vast space between galaxies, filled with diffuse gas and dark matter. The Fermi bubbles provide us with a unique opportunity to study this enigmatic region, as they interact with the intergalactic medium in ways that we are only beginning to understand. The high-energy particles within the bubbles could be interacting with the surrounding gas, transferring energy and creating cosmic rays that propagate through the space between galaxies. This would make the Fermi bubbles a key piece of the puzzle in understanding the behavior of matter on the largest scales. The energy released by the Fermi bubbles has the potential to influence the broader environment around them. As the particles within the bubbles interact with the surrounding gas, they may trigger a variety of processes that affect the surrounding environment. For example, they could heat the gas, preventing it from cooling and condensing into new stars. In this way, the bubbles may play a role in regulating star formation, not just within the Milky Way but potentially across other galaxies as well. The energetic outflows could prevent new stars from forming in certain regions, leading to the creation of what is known as a starless zone, an area where no new stars are born. This could have far-reaching implications for our understanding of galaxy formation and the life cycle of stars. The connection between the Fermi bubbles and galactic feedback mechanisms is another area of intense study. Feedback processes are key to understanding the evolution of galaxies and their surrounding environments. These processes involve the exchange of energy between different components of a galaxy, such as stars, gas, and the supermassive black hole at the galaxy's center. The Fermi bubbles may provide evidence for how energy is transferred between the black hole and the surrounding gas, influencing the galaxy's overall structure and behavior. The bubbles themselves may act as a feedback mechanism, either stimulating or suppressing star formation, depending on how the energy is distributed within the galaxy. As we continue to probe deeper into the mysteries of the Fermi bubbles, it is crucial to consider their broader implications for the universe's evolution. These bubbles are not just localized phenomena but part of a much larger network of cosmic events and structures. They represent the complex interplay between black holes, galaxies, and the intergalactic medium. Understanding the Fermi bubbles in the context of these interactions is essential for gaining a more holistic view of the universe. The study of the Fermi bubbles is also pushing the boundaries of our technological capabilities. Observing these massive structures requires advanced instruments that can capture high-energy radiation and study the most extreme environments in the universe. As technology advances, we may develop even more sophisticated instruments that can provide us with a deeper understanding of the physical processes that create these bubbles. New space telescopes, such as the James Webb Space Telescope, and advanced ground-based observatories will play a pivotal role in this research, offering a new generation of observational tools that will allow us to study the universe in greater detail. One of the key challenges in studying the Fermi bubbles is the complexity of the physical processes involved. The bubbles themselves are the result of a combination of factors, including the energy emitted by the supermassive black hole, the dynamics of the surrounding gas, and the magnetic fields that permeate the region. These factors interact in ways that are still not fully understood, and piecing together the details of these interactions requires careful analysis and interpretation of the data. However, as researchers continue to collect more data and develop better models of these processes, we can expect to gain a clearer picture of the forces at work. In addition to understanding the bubbles themselves, scientists are also working to understand the implications of their discovery for other areas of astrophysics. For example, the study of the Fermi bubbles has important implications for our understanding of cosmic rays, the high-energy particles that travel through space. The gamma-ray emissions from the bubbles are believed to be related to the acceleration of cosmic rays, and studying these emissions could provide valuable insight into how cosmic rays are created and how they propagate through the universe. This could have important consequences for our understanding of particle physics, astrophysics, and even the origins of life in the universe. As we explore these new frontiers, it is important to recognize that the Fermi bubbles are just one example of the many mysteries that remain to be uncovered in the cosmos. The universe is full of enigmatic phenomena, many of which challenge our current understanding of physics and the laws that govern the cosmos. The study of the Fermi bubbles is a key part of this ongoing quest for knowledge, offering us a glimpse into the complex and dynamic nature of the universe. With each new discovery, we are not only learning more about the Fermi bubbles themselves but also gaining a deeper understanding of the fundamental forces that shape the cosmos. In the coming years, as observational technologies improve and our understanding of the universe deepens, we can expect to learn even more about the Fermi bubbles and their role in the larger cosmic framework. Whether it is through the study of other galaxies, the investigation of cosmic rays, or the exploration of feedback mechanisms, the Fermi bubbles will continue to be a source of fascination and discovery for scientists and astronomers alike. The mysteries of the Fermi bubbles are far from being fully solved. As new data comes in and as our models of the universe evolve, we will continue to unravel the secrets of these enigmatic structures. They are a testament to the complexity and wonder of the universe, and their study will undoubtedly shape the future of astrophysics for years to come. With each passing year, we grow closer to understanding the nature of the Fermi bubbles and the forces that drive their creation. And as we do, we will continue to push the boundaries of human knowledge, expanding our understanding of the cosmos and our place within it. The quest to understand the Fermi bubbles is part of the larger exploration of high-energy astrophysical phenomena that can have profound implications not just for our understanding of the Milky Way but for galaxies everywhere. As our technology advances, we're able to look further and with greater precision, opening up new avenues for uncovering the secrets of the universe. The more we study these bubbles, the more we realize that their effects are not limited to just their immediate surroundings. They offer a window into processes that may be happening in countless other galaxies across the universe. One of the most intriguing aspects of the Fermi bubbles is the potential role they play in the broader cosmic ecosystem. Their interaction with the surrounding interstellar medium, composed of gas and dust, may influence star formation and the overall evolution of the galaxy. As the energy from the supermassive black hole's jets disperses outward into space, it can prevent the cooling of the gas, thus inhibiting star formation. This is significant because star formation is the lifeblood of galaxies, driving the creation of new elements and contributing to the dynamics that shape galaxies over time. The Fermi bubbles, by possibly halting or slowing this process, could provide a new mechanism by which galaxies regulate their own evolution. However, there is another side to this picture. While the Fermi bubbles may act to suppress star formation in some regions, they could also be contributing to the enrichment of the surrounding gas. When the energetic particles emitted by the supermassive black hole interact with the gas in the galaxy, they may cause it to heat up and ionize. This process can lead to the formation of heavier elements, which can then be spread throughout the galaxy and potentially even to other galaxies, playing a role in the process known as cosmic chemical evolution. In essence, the Fermi bubbles may act as a cosmic recycling mechanism, redistributing matter across the galaxy and possibly even influencing the formation of future generations of stars. As this process unfolds, it contributes to the overall health and life cycle of the galaxy. But the specifics of how these bubbles interact with their environment and shape the galaxy's evolution remain one of the many unanswered questions in modern astrophysics. The study of the Fermi bubbles is closely linked to the study of cosmic rays, those high-energy particles that travel through space at nearly the speed of light. Cosmic rays are believed to be created by some of the most energetic events in the universe, such as supernovae, gamma-ray bursts, and the outflows from supermassive black holes. The gamma-ray emissions observed from the Fermi bubbles suggest that cosmic rays may be a crucial component in the formation and evolution of these structures. By studying the Fermi bubbles, we may gain new insights into the processes that accelerate cosmic rays and how they travel across vast distances. This could help us understand not only the nature of cosmic rays but also how they interact with the interstellar and intergalactic medium, influencing the evolution of galaxies and even the broader structure of the universe. But beyond the bubbles themselves, the study of these high-energy phenomena opens up even bigger questions about the fundamental nature of the universe. What causes these massive outflows of energy? How do the magnetic fields, gas, and gravitational forces in the central regions of galaxies interact to produce such extraordinary structures? As we continue to observe and analyze the Fermi bubbles, we are diving into the very heart of some of the most mysterious and powerful forces in the cosmos. The possibility that the Fermi bubbles are connected to broader cosmic phenomena leads us to consider their place in the greater narrative of galaxy evolution. Supermassive black holes are thought to play a central role in this process, influencing the formation and growth of galaxies in ways that we are only beginning to understand. By observing the effects of the Fermi bubbles on their surrounding galaxies, we may be able to unlock new insights into the mechanisms by which black holes shape the lives of the galaxies they inhabit. While we've made significant strides in understanding the Fermi bubbles, there's still much to uncover. With advancements in both observational techniques and theoretical models, we are poised to make significant progress in the years ahead. The data provided by telescopes like Fermi and the James Webb Space Telescope will likely continue to provide critical information that will help researchers piece together the puzzle of the Fermi bubbles. As we delve deeper into the study of these enigmatic structures, one of the key areas of focus will be their connection to other high-energy phenomena, such as active galactic nuclei and quasars. These objects, which are powered by supermassive black holes at their centers, are known to emit enormous amounts of radiation and can influence their surrounding environment in profound ways. The Fermi bubbles may be related to these processes, providing us with clues about how these extreme environments work and how they affect the larger-scale evolution of galaxies. In the future, we may also see more detailed studies of the magnetic fields that surround the supermassive black holes in the centers of galaxies. Magnetic fields are thought to play a crucial role in the formation of structures like the Fermi bubbles, as they can channel the flow of particles and influence the way energy is distributed throughout the galaxy. By understanding these magnetic fields and their behavior, we may gain new insights into the underlying physics of these high-energy phenomena. There is also the question of whether the Fermi bubbles are a temporary feature or if they represent a more stable, long-term phenomenon. Some researchers have suggested that the bubbles may be the result of a particularly intense outburst from the supermassive black hole at the center of the Milky Way, while others believe that the bubbles may be part of a more ongoing process. If they are temporary, this could have significant implications for how we understand the life cycle of supermassive black holes and their impact on their host galaxies. Whatever the answers may be, one thing is certain: the Fermi bubbles remain one of the most captivating and mysterious phenomena in the universe. The study of these structures has the potential to unlock a wealth of knowledge about the most extreme environments in space, shedding light on everything from the role of black holes in shaping galaxies to the nature of cosmic rays and the evolution of the universe itself. The Fermi bubbles are a reminder of how much we have yet to learn about the universe, and how much is still waiting to be discovered. As we continue to explore the cosmos and push the boundaries of our knowledge, we will undoubtedly find more clues that will help us solve the mysteries of these enigmatic structures. The journey of discovery is far from over, and the Fermi bubbles may be just one of many cosmic phenomena that will help shape our understanding of the universe for generations to come. As the scientific community delves deeper into the investigation of the Fermi bubbles, new technologies and methodologies are constantly emerging, providing us with unprecedented access to previously inaccessible realms of space. Instruments like the Fermi Gamma-ray Space Telescope, which was launched in 2008, have been instrumental in detecting the gamma-ray emissions from the Fermi bubbles. This high-tech telescope is specifically designed to observe the highest energy gamma rays in the universe, allowing us to analyze phenomena that would otherwise be completely invisible. The Fermi bubbles, shining brightly in this energy range, present us with an excellent opportunity to explore how these enigmatic structures are formed and how they interact with the surrounding medium. The interaction between the Fermi bubbles and the surrounding interstellar medium offers a key piece of the puzzle in understanding these structures. The bubbles are believed to be composed of hot, diffuse gas, and the supermassive black hole at the center of the Milky Way likely plays a critical role in their formation. The process by which the bubbles grow and evolve could be influenced by several factors, including the rotation of the black hole, the magnetic fields in the region, and the flow of material from the galactic center. To study these processes in greater detail, scientists rely on a combination of observational data from various telescopes and models that simulate the behavior of these complex systems. By combining observations across different wavelengths, from gamma rays to X-rays, infrared, and even radio waves, researchers can create a more complete picture of what is happening within and around the Fermi bubbles. This multi-wavelength approach is essential because each type of radiation provides unique insights into different aspects of the structure. The bubbles themselves are not a single, static feature. They are dynamic and evolving over time. The rapid outflows of energy and matter that give rise to these structures can change the characteristics of the surrounding gas and magnetic fields, making it difficult to pinpoint exactly how long the bubbles have been in existence, or what their ultimate fate will be. Some researchers have even speculated that the bubbles could be related to other high-energy processes, such as the outflows seen in other active galactic nuclei or the formation of cosmic jets. As we explore the potential origins of the Fermi bubbles, one intriguing hypothesis is that the supermassive black hole at the center of the Milky Way has been periodically ejecting material in violent bursts. These bursts, known as active galactic nucleus (AGN) outbursts, can release enormous amounts of energy, producing high-energy particles and radiation that can create vast bubbles in the surrounding interstellar medium. If this is the case, the Fermi bubbles may be the result of multiple outbursts over millions or even billions of years, building up to form the structures we see today. One of the challenges in studying these outflows is that the gas and dust in the galaxy's central region are dense and obscured by various forms of interstellar dust. This makes it difficult to obtain a clear view of the central black hole and the region where the bubbles originate. However, by studying the high-energy emissions from the bubbles, we can gain valuable clues about what is happening in the galaxy's heart. The mystery of the Fermi bubbles also ties into broader questions about the evolution of the Milky Way itself. Understanding how the black hole's activity influences the dynamics of the surrounding galaxy is a key area of research. The central region of the Milky Way is a turbulent, high-energy environment where gas, stars, and dark matter interact in complex ways. The Fermi bubbles may be a reflection of the immense gravitational and magnetic forces at work in this chaotic region. One of the most fascinating aspects of the Fermi bubbles is the possibility that they are not unique to our galaxy. In fact, other galaxies with similar characteristics, particularly those with active galactic nuclei, may harbor their own versions of these enigmatic structures. As we study the Milky Way and its Fermi bubbles in greater detail, we may discover that this phenomenon is common throughout the universe. This could lead to new insights into the processes that govern galaxy formation and evolution, as well as the role that supermassive black holes play in shaping the galaxies they inhabit. In addition to their role in galaxy evolution, the Fermi bubbles may also have implications for our understanding of the universe on an even larger scale. For example, by studying the bubble's energy emissions, we can learn more about the distribution of cosmic rays throughout the galaxy. Cosmic rays are a major component of the high-energy particles that pervade space, and they can have a significant impact on the surrounding interstellar medium. Understanding the nature and origin of these particles could help us better understand how energy is distributed throughout the universe and how different astrophysical processes contribute to the larger cosmic environment. Another interesting aspect of the Fermi bubbles is their potential connection to the formation of supermassive black holes in other galaxies. Supermassive black holes are thought to reside at the centers of most galaxies, but their formation and growth remain largely a mystery. By studying the Fermi bubbles, we may be able to gain insights into the conditions that lead to the formation of these massive objects and how they evolve over time. Understanding the interplay between the black hole and the surrounding gas is crucial for understanding how these systems grow and develop. One of the challenges in understanding the Fermi bubbles is the complex relationship between the black hole, the gas, and the magnetic fields in the central region of the galaxy. The black hole's gravitational forces create intense pressure on the surrounding gas, and the magnetic fields help to direct the flow of particles and energy. The exact mechanisms that control the formation and expansion of the bubbles are still not fully understood, but research is ongoing to develop models that can explain these phenomena in greater detail. Despite the challenges, the study of the Fermi bubbles is helping to refine our understanding of the Milky Way and the broader universe. These structures are providing us with a new way to explore the high-energy processes at work in our galaxy and other galaxies throughout the cosmos. By continuing to observe the Fermi bubbles and improve our models of the underlying physics, we are opening up new avenues of discovery that will likely reveal even more surprising and profound mysteries in the future. As we continue our exploration of the Fermi bubbles, it becomes increasingly clear that these structures offer a window into the most extreme and energetic processes occurring within the Milky Way. Their sheer size and power present an opportunity to test our understanding of galactic dynamics and the behavior of supermassive black holes in ways that were previously unimaginable. With each new discovery, scientists are developing more refined models of how galaxies evolve and how their central black holes interact with the surrounding environment. One of the most critical aspects of studying the Fermi bubbles is the way in which they provide insight into the mechanisms of high-energy particle acceleration. Gamma rays, which are the primary form of energy emitted by the bubbles, are produced by highly energetic particles such as protons and electrons. These particles are accelerated to nearly the speed of light in what is known as a shock acceleration process. In this process, the particles gain energy by being pushed to higher velocities by shock waves or magnetic fields in their vicinity. This mechanism is thought to be responsible for the formation of cosmic rays, high-energy particles that travel vast distances through space. The study of the Fermi bubbles allows scientists to investigate this process in greater detail and gain a deeper understanding of how cosmic rays are generated and distributed throughout the galaxy. The nature of the gamma-ray emissions from the Fermi bubbles is particularly intriguing because they provide a direct glimpse into the high-energy particle interactions that are taking place in the galactic center. Gamma rays are the highest energy form of electromagnetic radiation, and they are often produced in extreme environments, such as those surrounding black holes or neutron stars. The fact that the Fermi bubbles emit such intense gamma rays suggests that the processes occurring in this region of the Milky Way are truly extraordinary. Some researchers have even suggested that the gamma rays could be a sign of interactions between the bubbles and the dark matter that is believed to permeate the galaxy. This connection is still speculative, but it highlights the potential for the Fermi bubbles to reveal important insights into the composition and behavior of dark matter, one of the most elusive and mysterious substances in the universe. As we investigate the origins of the Fermi bubbles, it is important to consider the broader context of galactic activity. The Milky Way is not an isolated system. It is part of a vast cosmic network of galaxies, many of which are actively evolving and undergoing similar high-energy phenomena. The study of the Fermi bubbles not only helps us understand our own galaxy, but it also provides valuable clues about the behavior of galaxies across the universe. By comparing the Fermi bubbles to similar structures found in other galaxies, scientists can begin to identify common patterns and processes that govern the formation and evolution of such features. This comparative approach is essential for understanding the role of supermassive black holes in shaping the structure and dynamics of galaxies. One of the key challenges in studying the Fermi bubbles is the complexity of the data involved. The bubbles themselves are not easily observed, as they are situated in the dense, dusty region at the center of the Milky Way, which obscures our view from Earth. Moreover, the gamma rays emitted by the bubbles are often accompanied by other forms of radiation, such as X-rays and infrared light, which can complicate the interpretation of the data. However, advances in telescope technology, such as the Fermi Gamma-ray Space Telescope and other observatories, have enabled researchers to overcome some of these obstacles and obtain more detailed and accurate observations of the bubbles. These observations have provided a wealth of information about the structure, energy, and behavior of the Fermi bubbles, but much remains to be discovered. In addition to the challenges posed by the complex data, there are also uncertainties regarding the precise nature of the processes that give rise to the bubbles. While the most widely accepted explanation is that the Fermi bubbles are the result of activity from the supermassive black hole at the center of the Milky Way, alternative hypotheses are also being explored. Some researchers have suggested that the bubbles could be the product of stellar winds or supernova explosions in the galactic center, rather than the result of black hole activity. Other models propose that the bubbles may be connected to the interaction between the galactic magnetic field and the surrounding gas. While the black hole hypothesis remains the most popular, further research is needed to determine whether other mechanisms could be at play. As scientists continue to refine their models and gather more data, they are gaining a deeper understanding of the Fermi bubbles and their role in the larger context of galactic evolution. The study of these structures offers a glimpse into the forces that shape the universe, and the more we learn about them, the clearer it becomes that the Fermi bubbles are a key to unlocking many of the mysteries of the cosmos. They challenge our understanding of how galaxies evolve, how supermassive black holes influence their surroundings, and how high-energy particles are accelerated and distributed throughout the galaxy. By studying these enigmatic structures, we are not only learning more about the Milky Way, but also gaining valuable insights into the processes that govern the formation and behavior of galaxies throughout the universe. The Fermi bubbles, in their vast and enigmatic grandeur, stand as one of the most fascinating mysteries in modern astrophysics. As our understanding of these structures deepens, we may find that they hold the answers to some of the most profound questions about the universe. How do supermassive black holes influence the galaxies they inhabit? What role do dark matter and cosmic rays play in the evolution of galaxies? What can we learn about the behavior of high-energy particles in the extreme environments of the galaxy's center? These are just some of the questions that the study of the Fermi bubbles may help us answer. As new discoveries continue to be made and our observational capabilities improve, it is likely that the Fermi bubbles will continue to be a source of fascination and insight for many years to come. As we continue to investigate the Fermi bubbles, their significance in the broader cosmic context grows more apparent. Beyond their stunning size and their mysterious origins, these bubbles provide an unparalleled opportunity to study the intricate dance between energy, matter, and gravity in one of the most extreme environments known to humanity. The sheer scale and power of the Fermi bubbles make them a unique object of study, one that could redefine how we think about galactic dynamics. One of the most intriguing aspects of the Fermi bubbles is their potential to unlock the secrets of high-energy astrophysics. These bubbles are not just unusual structures. They are the direct result of high-energy processes that are not yet fully understood. The acceleration of particles to nearly the speed of light, the formation of shock waves, and the interaction of these particles with magnetic fields all come together in a complex interplay that drives the behavior of the bubbles. In many ways, the study of the Fermi bubbles is a window into some of the most fundamental forces at play in the universe, including the relationship between gravity, electromagnetism, and high-energy particles. While the central black hole at the Milky Way's core remains the leading candidate for the source of the Fermi bubbles, new models continue to emerge, exploring alternative mechanisms for their formation. One promising theory suggests that the bubbles could be the result of galactic outflows caused by massive star formation in the galaxy's center. In this scenario, the combined force of stellar winds and supernova explosions could push gas and dust away from the galactic core, creating the powerful jets and shock waves responsible for the bubbles. This hypothesis could also explain the observed structure of the bubbles, as the outward flow of gas might cause the bubbles to extend symmetrically above and below the plane of the Milky Way. However, this theory remains under investigation, and further observations will be necessary to determine its validity. Another important consideration in studying the Fermi bubbles is the role of the galactic magnetic field. Magnetic fields are present throughout the galaxy and play a significant role in shaping the behavior of charged particles. In fact, the Fermi bubbles may be heavily influenced by the complex magnetic field structure at the galactic center. Some researchers have proposed that the bubbles are the result of interactions between the supermassive black hole and the magnetic fields that permeate the region. These interactions could accelerate particles to high energies, causing them to emit gamma radiation as they travel through the magnetic field lines. This model underscores the importance of magnetic fields in the overall dynamics of the Fermi bubbles and suggests that the study of these structures could also offer insights into the behavior of galactic magnetic fields. Despite these alternative hypotheses, the black hole-driven model remains the most widely accepted explanation for the formation of the Fermi bubbles. The supermassive black hole at the center of the Milky Way, known as Sagittarius A*, is thought to have gone through periods of intense activity in the past. During these phases, the black hole could have released massive amounts of energy in the form of jets and outflows, which might have created the Fermi bubbles. These outflows would have been propelled by the immense gravitational forces exerted by the black hole, and the resulting shock waves would have propagated outward, forming the observed bubbles. The current quiescent state of Sagittarius A* may be one reason why the bubbles are still observable today, despite the fact that their creation may have occurred millions of years ago. The connection between the Fermi bubbles and the supermassive black hole also raises important questions about the long-term behavior of galaxies. It is believed that supermassive black holes play a critical role in the evolution of galaxies, influencing their shape, structure, and star formation activity. The energy released by black holes, in the form of jets, outflows, and radiation, can have a profound impact on the surrounding gas and dust, heating and expelling material that might otherwise have contributed to future star formation. This process, known as feedback, is thought to be an essential component of galaxy evolution. The Fermi bubbles may provide direct evidence of this feedback mechanism in action, allowing scientists to study how black holes shape the evolution of galaxies over time. Moreover, the study of the Fermi bubbles has profound implications for our understanding of dark matter. Dark matter is an elusive substance that makes up a significant portion of the universe's mass but does not interact with light in the same way as ordinary matter. Although we cannot directly observe dark matter, its presence is inferred through its gravitational effects on visible matter. Some researchers have suggested that the gamma-ray emissions from the Fermi bubbles might be partially caused by interactions between dark matter particles. This idea, while still speculative, provides an exciting avenue of research, as it could offer indirect evidence of dark matter's existence and help us learn more about its properties. The potential link between the Fermi bubbles and dark matter has sparked a wave of interest in the scientific community, and further study of these bubbles could be key to unlocking some of the greatest mysteries of modern physics. The Fermi bubbles are also a fascinating subject of study for their implications in cosmology. They serve as a reminder of the dynamic and ever-changing nature of galaxies. The processes that shape the Milky Way are ongoing and complex, and the Fermi bubbles offer a glimpse into the powerful forces at work within our own galaxy. As we continue to observe and analyze these structures, we may begin to uncover more about the ways in which galaxies evolve and interact with their environments. By studying the Fermi bubbles in the context of other galaxies, we can gain a more comprehensive understanding of the universal processes that govern galactic behavior. The Fermi bubbles stand as one of the most mysterious and fascinating phenomena in the Milky Way. Their size, power, and enigmatic origins have captured the imagination of astronomers and astrophysicists, sparking new theories and ideas about the nature of galaxies, black holes, and high-energy particle processes. As research into the Fermi bubbles continues, we are sure to learn more about the fundamental forces that govern the universe and the role that our galaxy plays in the grand cosmic scheme. The study of these bubbles not only enhances our understanding of the Milky Way but also sheds light on the broader mysteries of the cosmos. The more we discover about the Fermi bubbles, the more we realize how much there is yet to learn about the universe that lies beyond. The potential implications of the Fermi bubbles extend far beyond the confines of the Milky Way. As we venture deeper into understanding these structures, one of the most exciting possibilities is how they might inform our understanding of other galaxies and their central supermassive black holes. Galaxies with similar structures may harbor their own hidden Fermi-like bubbles, and studying those could reveal new insights into galactic formation, evolution, and the impact of black holes on their host galaxies. Understanding the Fermi bubbles also opens up avenues for understanding more about the broader mechanics of galaxy cores. In particular, researchers are deeply interested in the feedback mechanisms at play between the black hole at the galactic center and its surroundings. This process, which essentially regulates the life cycle of a galaxy, plays a crucial role in star formation, the distribution of interstellar gas, and the overall dynamics of galactic evolution. The bubbles may be the direct result of such feedback, suggesting that the energy released from the galactic center, whether in the form of supermassive black hole activity or other high-energy phenomena, has a profound impact on shaping the structure and behavior of the Milky Way. Another important consideration is how the gamma-ray emissions from the Fermi bubbles may provide a clue to the nature of cosmic rays. Cosmic rays, which are high-energy particles traveling through space, have long been a subject of intense study. They are thought to originate from various sources, including supernovae, active galactic nuclei, and possibly even dark matter annihilations. The study of the Fermi bubbles may provide a direct observation of how such particles are accelerated to near-light speeds and how they interact with the interstellar medium. By understanding these interactions, we could gain a deeper insight into the processes that govern high-energy astrophysical phenomena and their role in shaping the universe. As the Fermi bubbles are explored in greater detail, one cannot overlook the role that new technologies and observational tools play in uncovering the secrets of the cosmos. The launch of more advanced space telescopes, such as the James Webb Space Telescope, JWST, promises to offer unprecedented views of the universe, with a focus on infrared wavelengths that are especially useful in studying distant and hidden cosmic phenomena. These advancements will allow astronomers to examine the Fermi bubbles with greater resolution, enabling them to probe their structure, composition, and energy sources with unparalleled detail. The combination of improved instrumentation and new theoretical models could lead to a breakthrough in our understanding of these enigmatic structures. The role of observational data is key to unlocking the mysteries of the Fermi bubbles, and space-based telescopes like the Fermi Gamma-ray Space Telescope remain instrumental in collecting invaluable information. Since its launch in 2008, the Fermi Gamma-ray Space Telescope has provided essential insights into gamma-ray emissions, shedding light on the composition and behavior of objects like the Fermi bubbles. Its observations have revealed the vast size of the bubbles and their striking symmetry, but the full range of gamma-ray emissions across different wavelengths still holds many secrets. By analyzing the data from these telescopes, scientists can continue to refine their models and hypotheses, testing various theories of how the Fermi bubbles came to be and what they can tell us about the Milky Way's past, present, and future. Moreover, the study of the Fermi bubbles raises important questions about the future of our galaxy. The energy released by the central black hole and the interaction of its jets with the surrounding gas and dust may play a significant role in the long-term evolution of the Milky Way. If the current state of the bubbles is indicative of a cyclical process, it could suggest that the supermassive black hole at the center of the galaxy undergoes bursts of activity over vast timescales. This raises the possibility that the Milky Way could continue to experience periods of energetic outbursts, potentially leading to further changes in the structure and star formation rates within the galaxy. The Fermi bubbles, in this sense, could be viewed as a window into the ongoing processes that shape our galaxy, offering a glimpse of its future evolution. Additionally, the Fermi bubbles might provide insights into the future of the broader cosmic environment. These massive structures are not confined to our galaxy. Similar phenomena may exist in other galaxies as well, potentially offering clues about the commonality of such structures in the universe. If the formation of the Fermi bubbles is a recurring process, it could suggest that active galactic nuclei, AGN, and their associated jets play a critical role in the evolution of galaxies across the universe. Furthermore, understanding the Fermi bubbles in this context could help scientists make predictions about the behavior of other galaxies, allowing them to anticipate the kinds of energetic outbursts and feedback mechanisms that could shape the evolution of galaxies in distant regions of space. The interaction between the Fermi bubbles and the intergalactic medium is another avenue of exploration. The bubbles extend far beyond the confines of the Milky Way's disk, pushing the boundaries of the galactic environment and influencing the surrounding space. These structures may have a significant impact on the distribution of gas and dust in the intergalactic medium, affecting star formation in neighboring galaxies. The Fermi bubbles could also serve as a means of transferring energy from the galactic center to the outer reaches of the galaxy, potentially providing new insights into the mechanics of galactic winds and their role in shaping the intergalactic environment. This broader interaction between galaxies and their surroundings could also hold the key to understanding the overall evolution of cosmic structures. In the search for a complete understanding of the Fermi bubbles, one cannot ignore the role of simulations and computational models. Astrophysical simulations have become an essential tool in exploring the complex interactions that govern the behavior of these structures. By using powerful computers to model the dynamics of the bubbles, researchers can test various hypotheses and refine their understanding of the processes involved. Simulations allow scientists to recreate the conditions present in the galactic core and observe how different factors, such as the black hole's activity, the distribution of gas, and the strength of magnetic fields, influence the formation and behavior of the Fermi bubbles. These models provide a theoretical framework that complements observational data, helping to bridge the gap between theory and observation. The study of the Fermi bubbles is also significant for the broader field of astrophysics. By investigating the high-energy processes that govern their formation, scientists can gain insights into other extreme astrophysical phenomena, such as active galactic nuclei, gamma-ray bursts, and the behavior of matter in the vicinity of supermassive black holes. The Fermi bubbles serve as an ideal laboratory for studying these processes, offering a direct view of how energy is transferred through space and how it influences the surrounding environment. As more data becomes available and our understanding of the bubbles deepens, we may uncover new connections between these structures and other cosmic phenomena, ultimately advancing our knowledge of the universe and its most mysterious forces. The Fermi bubbles are a fascinating and enigmatic feature of the Milky Way, offering a glimpse into the powerful and complex processes that govern the heart of our galaxy. Their size, energy, and mysterious origins make them an essential subject of study in modern astrophysics. Whether caused by the activity of the supermassive black hole at the galaxy's center, galactic outflows, or interactions with magnetic fields, the Fermi bubbles provide valuable insights into the dynamics of the Milky Way and its long-term evolution. As researchers continue to probe these structures using advanced observational tools, simulations, and new theories, the Fermi bubbles are sure to remain a central focus of scientific inquiry, revealing new secrets about the fundamental forces that shape the universe. The journey of uncovering the full story behind the Fermi bubbles is far from over. As astrophysicists continue to study these structures, they are met with new mysteries that demand further exploration. One of the key questions that remains unanswered is how the Fermi bubbles formed in the first place. While many of the leading theories focus on the activity of the supermassive black hole at the center of the Milky Way, there are still several possibilities to consider. Could these bubbles be the result of a unique cosmic event, such as a collision between two massive objects, or are they a natural byproduct of the ongoing processes occurring in the galactic core? Only time and further research will tell. To answer these questions, scientists are relying on an ever-expanding arsenal of tools and techniques. Advanced simulations, for example, are allowing researchers to test different models of how the Fermi bubbles might have formed. These models simulate everything from the dynamics of gas and magnetic fields in the galactic center to the behavior of high-energy particles that might be responsible for the gamma-ray emissions we observe. As the simulations become more refined and more data becomes available, researchers will be able to compare the results with actual observations to better understand the origin of these bubbles. The growing understanding of the Fermi bubbles is also helping to deepen our knowledge of the larger processes occurring throughout the Milky Way. As we know, the galaxy is constantly evolving, with stars being born, dying, and interacting in ways that can have dramatic effects on the surrounding environment. The Fermi bubbles might be a snapshot of one of these evolutionary phases, offering a rare glimpse into the powerful forces at play within our galaxy. By understanding these forces, we can better comprehend the future of the Milky Way and our place within it. Could the Milky Way eventually undergo another massive energetic outburst like the one that created the Fermi bubbles? If so, what would that mean for the future of the galaxy and the life it supports? These questions extend beyond the confines of our own galaxy. As scientists probe the nature of the Fermi bubbles, they are also developing new techniques for studying similar phenomena in other galaxies. There may be other galaxies out there with structures akin to the Fermi bubbles, and studying these could yield valuable insights into the processes that govern the evolution of galaxies across the universe. In this way, the Fermi bubbles offer a critical piece of the cosmic puzzle, helping scientists piece together the broader picture of galactic formation, evolution, and interaction. Moreover, the study of the Fermi bubbles also has implications for our understanding of the universe's energy balance. These bubbles represent an enormous amount of energy, much of which is emitted in the form of gamma rays. Understanding where this energy comes from, how it is distributed, and what role it plays in the overall dynamics of the Milky Way could help scientists better understand the processes that power the universe. The Fermi bubbles may not just be a local phenomenon within the Milky Way, but part of a larger cosmic cycle that dictates how energy is transferred between galaxies and even between the different components of a galaxy. One of the most intriguing aspects of the Fermi bubbles is their symmetry. The fact that they extend symmetrically above and below the galactic plane is a feature that has sparked much debate. It suggests that whatever process created the bubbles must have occurred in a way that imparted equal amounts of energy in both directions. This symmetry raises the possibility that the bubbles are the result of a feedback mechanism between the black hole at the center of the galaxy and the surrounding gas and dust. The energy released by the black hole could have caused a shockwave or outflow that pushed material outward, creating the bubble-like structures we see today. Understanding this feedback mechanism could shed light on the broader role that supermassive black holes play in shaping the galaxies they inhabit. However, the Fermi bubbles are not just a topic of interest for astronomers. Their discovery and subsequent study have also sparked interest in the broader field of physics. The gamma-ray emissions from the Fermi bubbles present an exciting opportunity for researchers to study the high-energy processes occurring in the galaxy. Gamma rays are one of the most energetic forms of light, and studying them can help scientists learn about the most extreme environments in the universe. In particular, the Fermi bubbles may offer new insights into the behavior of high-energy particles, such as cosmic rays, and how they interact with the interstellar medium. As researchers continue to study the Fermi bubbles, they are also looking for ways to improve the instruments used to observe them. While current telescopes, such as the Fermi Gamma-ray Space Telescope, have provided valuable data, there is always room for improvement. The next generation of space telescopes, such as the James Webb Space Telescope and the proposed Nancy Grace Roman Space Telescope, promise to provide even more detailed observations of the universe. These advancements could help astronomers study the Fermi bubbles in greater detail, enabling them to probe their structure, composition, and energy sources with unprecedented precision. With these new tools at their disposal, scientists will be able to test new hypotheses and refine their understanding of the Fermi bubbles and their role in the larger cosmic landscape. In the coming years, it's likely that the Fermi bubbles will remain a focal point of scientific inquiry. Their size, energy, and mysterious origins continue to captivate the imagination of astronomers, physicists, and space enthusiasts alike. As we learn more about these enigmatic structures, we are not only gaining insight into the workings of our own galaxy, but also into the fundamental forces that govern the universe. Whether caused by the activity of the supermassive black hole at the Milky Way's center, interactions with intergalactic matter, or some yet-to-be-discovered phenomenon, the Fermi bubbles offer a unique opportunity to study the most extreme conditions in the universe. The more we learn about them, the more we uncover about the nature of our universe, and the more we are reminded of just how much there is left to explore. With each new discovery, the Fermi bubbles bring us closer to understanding the forces that shape galaxies and the universe itself. Their existence challenges our understanding of the universe, offering a glimpse into the unseen structures and forces that operate on the largest scales. The Fermi bubbles are not just a curious feature of the Milky Way. They are a key to unlocking some of the deepest mysteries of the cosmos. As we continue to explore these enigmatic structures, we are reminded of the infinite possibilities that lie beyond the stars, waiting for us to uncover them. As scientists continue to peel back the layers of the Fermi bubbles' mystery, one of the critical areas of focus is the relationship between these structures and the broader environment of the Milky Way. The Fermi bubbles are not just isolated anomalies in space. They are embedded within the complex dynamics of the galaxy's interstellar medium. This medium is made up of gas, dust, and magnetic fields that permeate the galaxy, and the interaction between the bubbles and this environment could hold the key to understanding their formation. For one, the bubbles appear to be connected to the galactic wind, a continuous outflow of hot gas and energetic particles that emanates from the galactic center. This wind is thought to be generated by the intense activity around the supermassive black hole, which constantly draws in matter from its surroundings. The radiation from this black hole may be enough to heat nearby gas to the point where it expands outward in all directions, creating the structures we observe as the Fermi bubbles. However, the exact mechanics of how this galactic wind interacts with the interstellar medium remain unclear. Is the wind pushing against the gas in the galaxy's halo, creating the bubble-like structures? Or is the energy from the wind somehow being channeled into specific regions of the galaxy's halo, forming the bubbles as we see them? One of the major challenges in answering these questions is the difficulty in observing the galactic wind itself. Most of the gas involved in this process is invisible to ordinary telescopes because it exists at extremely high temperatures, making it hard to detect directly. Instead, astronomers have to infer its presence through indirect means, such as the observation of the Fermi bubbles' emissions and the behavior of surrounding gas. This complexity adds an extra layer of intrigue to the study of the Fermi bubbles. The fact that they seem to be an interaction between several different components of the galactic ecosystem, from the supermassive black hole at the center of the galaxy to the distant gas and dust at its outskirts, suggests that they could be an important piece of a much larger puzzle. They could offer clues not just about the evolution of the Milky Way, but about the behavior of galaxies in general. Are the Fermi bubbles an unusual feature of our galaxy, or do other galaxies exhibit similar structures? And if so, what does that tell us about the evolution of galaxies on a cosmic scale? One possibility that researchers are exploring is the idea that the Fermi bubbles might be a sign of a galaxy in transition. In the early stages of galactic evolution, galaxies often undergo intense bursts of star formation, during which large amounts of gas and dust are pushed outward, creating large-scale structures like the Fermi bubbles. These outflows may also play a role in regulating the amount of gas available for future star formation. In this sense, the Fermi bubbles might be part of the Milky Way's ongoing evolution, representing a phase in which the galaxy is shedding material and redistributing energy. If this hypothesis proves true, it could provide important insights into the processes that shape galaxies over billions of years. One intriguing piece of evidence that supports this idea is the fact that the Fermi bubbles appear to be relatively young structures. The energy released by the supermassive black hole at the center of the galaxy is thought to have been concentrated in this region relatively recently, on a timescale of just a few million years. This suggests that the Fermi bubbles are a product of relatively recent activity, which could have triggered a wave of galactic evolution. If the Milky Way is indeed undergoing such a transition, it could have profound implications for our understanding of how galaxies form and evolve. Perhaps the Milky Way is not a static, unchanging entity, but rather a dynamic system that is constantly evolving and adapting to new conditions. On the other hand, the Fermi bubbles could be the result of an ancient event that continues to reverberate through the galaxy. The outflows that created the bubbles may have been triggered by an event long ago, such as the merger of two galaxies or the accretion of a large amount of material by the supermassive black hole. The energy released by these events could have been sufficient to create the bubbles, which would then expand outward over millions or billions of years. In this scenario, the Fermi bubbles would be a remnant of a past galactic event, offering us a snapshot of the Milky Way's distant history. Regardless of their origin, the study of the Fermi bubbles is contributing to a much broader understanding of the universe. These enigmatic structures represent an intersection of many of the most exciting and mysterious phenomena in astrophysics. They are linked to the behavior of supermassive black holes, the dynamics of galactic winds, the properties of high-energy particles, and the evolution of galaxies themselves. By studying the Fermi bubbles, scientists are piecing together a narrative of the Milky Way's past, present, and future, while also shedding light on the broader processes that shape the universe as a whole. This growing body of knowledge has led to some truly exciting developments in the field of astronomy. As researchers continue to analyze the data from the Fermi Gamma-ray Space Telescope and other instruments, they are uncovering more details about the structure and behavior of the Fermi bubbles. For example, new observations have revealed that the bubbles are not perfectly symmetrical, with slight differences in their size and shape. These small variations could provide important clues about the physical processes that gave rise to the bubbles and how they interact with the surrounding gas. In addition, researchers are developing increasingly sophisticated models to simulate the formation and evolution of the Fermi bubbles. These models take into account everything from the distribution of gas and dust in the galaxy to the magnetic fields that shape the bubble's structure. By comparing the results of these simulations with actual observations, scientists can refine their understanding of the Fermi bubbles and test different hypotheses about their origins. One area of research that has shown particular promise is the study of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, and they are thought to be closely linked to the processes occurring within the Fermi bubbles. Some scientists believe that the bubbles may be a source of cosmic rays, which could explain the gamma-ray emissions observed in this region. By studying these particles in greater detail, researchers hope to uncover more information about the conditions within the bubbles and their connection to the broader cosmic environment. The continued exploration of the Fermi bubbles also has implications for the future of space exploration. As we develop more advanced telescopes and instruments, we will be able to study the bubbles in greater detail and learn more about their composition, structure, and energy sources. These discoveries could lead to new insights into the fundamental nature of the universe and the processes that govern the behavior of matter and energy on the largest scales. The Fermi bubbles may be one of the most exciting and mysterious phenomena in the Milky Way, and their study is sure to be a major focus of research for years to come. As we move forward, it's clear that the Fermi bubbles are not just a curiosity, but a window into the deeper workings of the universe. By continuing to explore these enigmatic structures, we are not only learning more about the Milky Way, but also about the fundamental processes that shape the cosmos itself. The more we uncover about the Fermi bubbles, the more we realize just how much there is left to discover. The universe is full of mysteries, and the Fermi bubbles are one of the most captivating and complex enigmas of all. As our exploration of the Fermi bubbles progresses, it's crucial to consider the broader implications of these findings. The connection between the bubbles and the galactic center, especially with the supermassive black hole, hints at how these dynamic structures could influence not only the Milky Way but galaxies in general. Understanding the Fermi bubbles is like decoding a secret language about how galaxies evolve, grow, and even change their behavior over cosmic timescales. What we are learning here could extend far beyond the boundaries of the Milky Way, offering universal insights that apply to countless other galaxies scattered across the vast reaches of the universe. It's important to keep in mind that the study of these gamma-ray bubbles isn't an isolated endeavor. Rather, it fits into a much larger narrative about the life cycle of galaxies. Galaxies are not stagnant, they undergo constant transformations, driven by internal forces like supermassive black holes, star formation, and the complex interplay of gas and dust. The Fermi bubbles provide one possible glimpse into this process, offering astronomers a rare opportunity to observe the aftereffects of a major event, a cosmic wind blowing outward from the core of the Milky Way, scattering energy and particles across a vast region of space. Moreover, these bubbles raise significant questions about the fundamental properties of the intergalactic medium. The hot gas that fills the bubbles likely extends far beyond the boundaries of our galaxy, reaching into the outskirts of the Milky Way's halo. This intergalactic gas, which is also part of the galactic ecosystem, plays a key role in the overall mass, dynamics, and evolution of galaxies. The Fermi bubbles, as large-scale outflows of energy and matter, may help scientists better understand how gas behaves in such extreme environments, and how it might contribute to galactic evolution on a more universal scale. What happens to the matter that gets ejected into space? Does it eventually return to the galaxy, or is it lost to the intergalactic void forever? Some researchers have suggested that studying these energetic outflows could also give us more information about the rate of star formation in the Milky Way and other galaxies. We know that galactic winds can suppress star formation by expelling the cold gas necessary to create new stars. Thus, these bubbles may be more than just a spectacular phenomenon. They could be playing a crucial role in regulating the growth and evolution of the Milky Way. This aspect of galactic evolution, while difficult to measure, could have significant consequences for our understanding of how galaxies evolve and age. The Fermi bubbles might also be part of a broader and more mysterious category of phenomena, those that seem to defy conventional understanding or classification. These bubbles, with their vast size, energetic properties, and intriguing emissions, suggest that we are just beginning to scratch the surface of what's possible in the universe. If we consider how such powerful phenomena could occur in a region as seemingly stable as the galactic center, it prompts further curiosity about the hidden mechanisms at work in other galaxies and celestial structures. What if the Fermi bubbles are just one of many similar phenomena scattered throughout the universe, each unique in its specifics but tied together by the same underlying principles? To better understand the Fermi bubbles, we must also examine the technologies that are allowing us to study them. Instruments like the Fermi Gamma-ray Space Telescope have enabled us to detect the high-energy gamma rays that emanate from these bubbles. But there's much more to learn about their precise composition, energy, and behavior. Advanced telescopes such as the upcoming James Webb Space Telescope, JWST, could provide even more detailed observations, potentially allowing us to peer into the heart of these enigmatic structures. The JWST's capabilities to observe in infrared wavelengths could offer a different perspective on the bubbles, revealing cooler gas and perhaps shedding light on the forces that drive their expansion. Additionally, the upcoming generation of space telescopes, including the Cherenkov Telescope Array, CTA, promises to provide greater sensitivity to gamma rays, enabling scientists to study the high-energy particle interactions occurring within the Fermi bubbles in unprecedented detail. As technology continues to advance, the puzzle of the Fermi bubbles will likely become clearer, and new insights into their nature and role in the galactic ecosystem will emerge. On the subject of cosmic rays, a topic that is heavily tied to the Fermi bubbles, there are still many open questions. As we learn more about the bubbles, we are also learning more about cosmic ray acceleration. Cosmic rays, which are high-energy particles that travel through space at nearly the speed of light, have been observed to originate from various astrophysical sources, including the Fermi bubbles. By studying the composition and behavior of these cosmic rays, researchers can better understand the underlying physical processes that generate these high-energy particles. The fact that the Fermi bubbles are such a significant source of cosmic rays suggests that they may be playing a major role in shaping the cosmic ray background in the Milky Way. However, studying cosmic rays presents its own challenges. These particles interact with magnetic fields as they travel through space, making it difficult to trace their exact origins. Understanding where cosmic rays are produced and how they interact with the galactic medium could give us a deeper understanding of the conditions within the Fermi bubbles and, more broadly, the processes at play in the galaxy's core. As scientists continue to refine their techniques and simulations, it's likely that they will uncover even more details about how cosmic rays are produced and how they contribute to the broader picture of galactic evolution. One of the more exciting aspects of studying the Fermi bubbles is that they represent an intersection of many different fields of astrophysics. The study of supermassive black holes, high-energy astrophysics, cosmic rays, and galactic evolution all converge in this one phenomenon. This makes the Fermi bubbles a prime area of study for astronomers, as they offer a rare opportunity to understand multiple facets of galactic dynamics in one concentrated region of space. As our understanding of these bubbles deepens, we will likely uncover new connections between these fields and gain a richer understanding of the universe's inner workings. This is why the Fermi bubbles are such an exciting subject of research. They force us to reconsider what we know about the universe and how galaxies, stars, black holes, and all the material in between interact. They are a testament to the dynamic, ever-evolving nature of the cosmos. While they remain enigmatic, they are also a beacon, calling us to explore further and unravel the mysteries of our galaxy and beyond. As the study of the Fermi bubbles progresses, we are likely to see new theories emerge. Perhaps future research will show that these bubbles are even more interconnected with other galactic phenomena than we initially thought. Maybe they play a key role in the long-term evolution of the Milky Way, affecting everything from the formation of new stars to the distribution of matter in the galaxy's halo. Or perhaps they will reveal new aspects of cosmic energy, offering clues to the fundamental laws of physics that govern our universe. Whatever the outcome, the Fermi bubbles will continue to be a focal point of astrophysical research. Each new discovery brings us closer to understanding the complex forces at work in the Milky Way and beyond. The Fermi bubbles are not just an anomaly in our galaxy. They are a glimpse into the profound and intricate processes that shape the cosmos itself. As we continue to investigate these enigmatic structures, we move closer to a future where we can answer some of the deepest questions in astrophysics. What exactly is the relationship between supermassive black holes and their surrounding environments? How do galactic winds shape the evolution of galaxies? What role do high-energy particles like cosmic rays play in the broader dynamics of space? The answers to these questions could transform our understanding of the universe in ways we cannot yet imagine. In the grand scheme of things, the Fermi bubbles are just one piece of a much larger puzzle. But they represent a critical part of our ongoing journey to unravel the mysteries of the universe, helping us piece together the story of the Milky Way and the fundamental forces that govern the cosmos. The Fermi bubbles, while still an active subject of study, have already captured the imagination of astronomers and the general public alike. Their discovery marked a momentous shift in how we perceive the central regions of galaxies, particularly the Milky Way. These bubbles, which extend well above and below the galactic center, challenge conventional understanding of galactic structure, dynamics, and energy. As we dive deeper into their mysteries, the focus of research has gradually expanded to include the broader implications these bubbles may have for the future of the Milky Way. If, as some theories suggest, the bubbles are the result of an immense eruption from the supermassive black hole at the galactic center, the scale of this event is truly awe-inspiring. Such outbursts, which release colossal amounts of energy, have the potential to shape the future of the galaxy itself. If the Fermi bubbles are the product of a past event, this leads to important questions about the ongoing activity of the black hole, such as whether it is in an active phase or has entered a period of quiescence. Understanding the cycles of activity and dormancy in supermassive black holes is crucial for predicting the long-term behavior of galaxies. The Milky Way, like all galaxies, is a dynamic, evolving system. The discovery of the Fermi bubbles suggests that this evolution is not only shaped by the more visible processes of star formation, supernovae, and stellar winds but also by more hidden, extreme phenomena occurring in the deep recesses of the galactic center. The behavior of supermassive black holes, which are thought to exist at the center of most large galaxies, is intimately connected to the surrounding environment. As we continue to study the Fermi bubbles, we may begin to see more connections between these central black holes and the large-scale structure of galaxies. It's possible that the energy produced by these supermassive black holes plays a significant role in regulating the dynamics of galaxies, influencing the way they form, evolve, and even die. Looking outward from the Milky Way, the question arises, are the Fermi bubbles unique to our galaxy, or are similar structures found in other galaxies as well? The discovery of these bubbles has sparked interest in searching for analogous phenomena in other galactic centers. If such structures exist elsewhere, they could provide us with valuable comparative data. By examining the similarities and differences between the Fermi bubbles and those found in other galaxies, we might be able to develop a more universal understanding of galactic activity. This search could lead to a breakthrough in our understanding of the behavior of supermassive black holes, cosmic rays, and galactic outflows. There is also the possibility that the Fermi bubbles are part of a larger family of cosmic structures that we have yet to fully categorize. The discovery of large-scale outflows in galaxies is not unprecedented. Similar structures have been observed in distant galaxies, though they are often smaller or less easily identifiable. The Fermi bubbles, however, are unlike any previously discovered feature within our galaxy due to their massive size and the energy they emit. Their discovery has therefore prompted astronomers to reassess their models of galactic activity, leading to new ideas about the types of energy outflows that may occur in galactic centers. In fact, the Fermi bubbles may be linked to a wide array of other cosmic phenomena, such as galactic winds, cosmic ray acceleration, and high-energy particle interactions. Researchers have begun to speculate that these bubbles may be connected to the broader galactic ecosystem. For instance, the bubbles may serve as a conduit for the release of energy that is generated within the galaxy's core. This energy could then influence the larger galactic environment by affecting the distribution of gas, dust, and stars. In this way, the Fermi bubbles could represent an essential process in the feedback loop that governs the evolution of galaxies. As we look at the Milky Way in its entirety, it's also worth considering the larger role that the galaxy plays in the cosmos. Galaxies are not isolated entities. They interact with each other in various ways. For example, the Milky Way is currently engaged in a cosmic dance with its neighbor, the Andromeda Galaxy, and in the distant future, these two galaxies will collide, merging into a single, larger galaxy. During such interactions, massive energy outflows could occur, potentially giving rise to new phenomena similar to the Fermi bubbles. Understanding these types of galactic interactions is crucial for predicting the long-term behavior of galaxies and for understanding how they evolve on both a local and cosmic scale. To fully grasp the significance of the Fermi bubbles, it is essential to keep in mind the broader implications of their study. While they provide a window into the hidden processes of the Milky Way, they also offer a glimpse into the more profound workings of the universe. The discovery of these bubbles challenges our current models of galactic evolution and forces us to reconsider how energy is distributed throughout galaxies. Their existence suggests that the central regions of galaxies are far more dynamic than we once thought, and that supermassive black holes may play an even more pivotal role in shaping the galaxies they inhabit. Another fascinating aspect of the Fermi bubbles is their potential connection to the ongoing search for dark matter. Dark matter, which makes up a significant portion of the universe's mass, has remained elusive, with its properties largely unknown. However, some theories suggest that the energy emitted by the Fermi bubbles could be related to the annihilation of dark matter particles. If dark matter does interact in such a way, the Fermi bubbles could provide crucial evidence of its existence, and help scientists refine their understanding of this mysterious substance. This is another avenue of research that could have profound implications for our understanding of the cosmos. In the coming years, as observational techniques continue to advance, it's likely that we will uncover even more details about the Fermi bubbles and their role in the Milky Way. New telescopes and instruments, such as the next generation of X-ray and gamma-ray observatories, will provide a wealth of data that could help scientists refine their models of galactic activity. With more detailed observations, we may be able to uncover previously hidden layers of information about the bubbles, such as their exact composition, the mechanics behind their formation, and their connection to other cosmic phenomena. These discoveries will not only advance our understanding of the Milky Way but could also shed light on broader questions about the nature of galaxies, black holes, cosmic rays, and the fundamental processes that govern the universe. Each new breakthrough brings us closer to answering questions that have puzzled astronomers for centuries, and the Fermi bubbles are poised to play a key role in this process. While much about the Fermi bubbles remains mysterious, one thing is certain: they are far from ordinary. These enigmatic structures are a testament to the complexity of the universe, reminding us that even in the most familiar regions of space, there are still countless secrets waiting to be uncovered. As we continue to study these massive, gamma-ray-emitting bubbles, we are embarking on a journey that will take us to the heart of galactic evolution and the very fabric of the cosmos. The Fermi bubbles are not just a unique feature of our galaxy. They are a profound reminder of the vast, uncharted territories that still lie ahead in the field of astrophysics. What they represent in terms of galactic activity, cosmic rays, and the behavior of supermassive black holes is only the beginning of a much larger story, one that continues to unfold with each new discovery. As technology advances and our understanding deepens, we are likely to find even more surprising revelations in the coming years. With every new observation, the Fermi bubbles are taking us one step closer to unlocking the true mysteries of the universe. The continued study of the Fermi bubbles opens the door to many potential revelations about the universe, with each new discovery adding more complexity to the structure and behavior of galaxies, black holes, and the universe itself. While much about these cosmic structures remains unclear, the very fact that they exist challenges traditional notions of how galaxies evolve. For years, the supermassive black hole at the center of the Milky Way has been understood primarily as a quiet giant, absorbing surrounding matter and occasionally emitting jets of material. However, the discovery of the Fermi bubbles has provided a stunning twist, offering a fresh perspective on the active role these black holes might play in shaping the broader cosmic landscape. The process by which the Fermi bubbles were formed and their precise relationship to the supermassive black hole in the Milky Way remains a subject of intense research. It is widely believed that these bubbles are the product of a massive outburst from the galactic core, powered by either the accretion disk surrounding the black hole or the energy released by its powerful jets. These jets, often associated with active galactic nuclei, AGN, have long been known to spew energetic material into space. But the scale and nature of this energy release in our galaxy, as manifested in the Fermi bubbles, is unprecedented. One of the leading hypotheses suggests that the Fermi bubbles are a result of a long-term process where the black hole expels material over a period of millions of years. The bubbles themselves are thought to represent a vast outflow of high-energy particles and radiation, much like the energetic jets observed in active galaxies. These outflows could have been triggered by a series of events, such as a sudden burst of activity from the supermassive black hole, a collision with another massive object, or even the interaction with the surrounding gas and dust in the galactic center. While these processes are still being modeled and refined, what is clear is that the Fermi bubbles are a powerful testament to the immense energy that can be released by even a relatively dormant black hole. Interestingly, the Fermi bubbles also provide valuable insights into the cosmic environment surrounding our galaxy. Observations of these structures, particularly their gamma-ray emissions, have revealed the distribution of high-energy particles in the galactic halo. The presence of these particles suggests that the bubbles are not just the result of black hole activity, but also part of a much larger process of galactic evolution. These particles, as well as the intense radiation emitted by the bubbles, could be influencing the behavior of the interstellar medium, which in turn could affect star formation rates and the overall dynamics of the Milky Way. Moreover, the discovery of the Fermi bubbles has prompted astronomers to look more closely at the broader implications of such outflows on the galactic ecosystem. In many ways, the energy expelled from the central regions of the galaxy might play a key role in regulating the balance between star formation, gas dynamics, and the accumulation of dark matter. Understanding these interactions, as well as the mechanisms behind the formation and expansion of these bubbles, could unlock important information about the past and future of our galaxy. What makes the Fermi bubbles even more intriguing is their potential connection to larger cosmic structures, such as galactic winds. These winds, which are known to occur in a number of galaxies, represent the large-scale outflow of gas and energy from the galactic center. Some scientists have hypothesized that the Fermi bubbles are part of a more complex galactic wind, with the energy released by the supermassive black hole contributing to the expansion and movement of gas and dust across the galaxy. If this is the case, the Fermi bubbles could be playing a key role in the regulation of the Milky Way's gas and dust, ultimately shaping the future of star formation and the growth of the galaxy itself. The search for other examples of Fermi bubbles in different galaxies is another exciting avenue of research. If similar structures are found in other galaxies, it would suggest that the phenomena observed in the Milky Way are not unique but part of a broader pattern across the universe. This could provide astronomers with a wealth of comparative data that could shed light on the processes that drive galactic evolution on a cosmic scale. Already, astronomers are investigating the presence of gamma-ray-emitting bubbles in other galaxies, and the results could revolutionize our understanding of galactic structure and dynamics. One of the most fascinating aspects of the Fermi bubbles is the potential link between their formation and the ongoing search for dark matter. As mentioned earlier, some researchers have speculated that the unusual gamma-ray emissions associated with the bubbles could be the result of dark matter annihilation. While dark matter remains one of the most elusive and mysterious substances in the universe, any direct or indirect evidence of its existence would be a monumental discovery in astrophysics. The possibility that dark matter plays a role in the formation of the Fermi bubbles adds an entirely new layer of complexity to this already intriguing puzzle. As the field of astrophysics continues to evolve, new technologies and observational methods will allow us to probe deeper into the nature of the Fermi bubbles and their connection to the broader structure of our galaxy. The next generation of space telescopes, such as the James Webb Space Telescope and the planned next-generation X-ray observatories, will provide even greater insight into these cosmic structures, offering the potential for breakthroughs that could answer many of the questions surrounding the bubbles. Furthermore, advancements in computational astrophysics will allow scientists to simulate the formation and evolution of structures like the Fermi bubbles with increasing accuracy. These simulations will provide valuable data that could help refine current theories about the processes at work in the galactic center, leading to a more detailed understanding of how such immense structures come into being. These simulations will also allow scientists to test different hypotheses, such as the relationship between the Fermi bubbles and dark matter, and explore how different factors might contribute to the formation of these enigmatic structures. The discovery of the Fermi bubbles represents a critical moment in the study of the Milky Way and the larger universe. They not only challenge existing theories of galactic evolution but also open up new avenues of exploration, from the role of supermassive black holes in galactic dynamics to the potential connections between these bubbles and dark matter. As we continue to observe and study the Fermi bubbles, it is likely that we will uncover new aspects of the universe's most profound mysteries, transforming our understanding of the cosmos in ways we can scarcely imagine. While much remains to be learned about the Fermi bubbles, one thing is certain: these cosmic structures are far more than just a scientific curiosity. They are a window into the dynamic, ever-changing nature of the universe and a reminder of the immense forces that shape the galaxies we call home. Whether they are the result of a massive outburst from the Milky Way's supermassive black hole or the manifestation of some other cosmic process, the Fermi bubbles stand as a testament to the complexity and mystery that continues to define the field of astrophysics. As new discoveries are made and new technologies are developed, we can only imagine what future research will reveal about the Fermi bubbles and the countless other mysteries that still await us in the vast expanse of space. The journey to unravel these cosmic enigmas has only just begun, and the answers we find along the way will undoubtedly reshape our understanding of the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.